Okay, since we are 2 minutes early, let me start by a summary of where we are and what we are going to try to do now. So we are in the middle of turbulent combustion. Okay, that's the first time we talk about that during this week. And I've shown you that there was a lot of phenomenological arguments about turbulent flames, but that ultimately what you are interested in is to model them. And so to model them, the first thing we said is that we would need either to time average the conservation equations or to space filter them, which is, from a formal point of view, the same operator that you see here, the tilde, that we would do that with Favre averaging, you know, this not so democratic way to count your votes. And that when we have finished averaging those equations, we realized that the averaged equations did not look like the instantaneous equations. They had additional terms. And we said that the whole problem of turbulent combustion was to find a way to model these two terms which were not there initially. The turbulent diffusion term, which comes from this term here that we have extracted here, and these correlations are not zero, and the mean reaction rate. And I have shown you how to build a very, very bad model, but this is the only one we have for this term, which is called the diffusion term, where we replaced this term by an expression which uses the gradient of the mean progress variable so that we could replace this term directly in the equations. So this term that we don't know, we replace it as a function of the gradient of theta. And I think someone asked me if there were proof that this thing was working. They actually proved that this thing is not working in many cases. And that's a term that you might want to remember. This term is linking the flux here to the gradient of theta. And we know that there are cases where even the sign is wrong. Okay, that's what we call counter-gradient diffusion. When turbulence is not very intense, a model like this will produce a result which has the wrong sign. Okay, we're not even talking about magnitude. The sign is wrong. But still, everyone's using it. Okay, no one in the community, well, no one, maybe 0.1% of the papers try to do something else. So we're all using this model. So there are good reasons for that, but I don't want to go into the details for the moment. Let's say that this is a Darwinian process. This is the only model which is used today. Now I want to talk about the second one. The second one is an average needed for this quantity. This is the instantaneous reaction rate of a flame, and now we need to average it or to filter it. And so you might think, oh, okay, that shouldn't be that difficult, but this has kept us busy for a long, long time. So let me show you where the problem is. This is the expression of the reaction rate as a function of temperature. And it is very nonlinear. So when you want to average it, that will lead to problems. So I will actually list quite a few models here that you will find in the codes that you use. And I will finish by actually an AI model because this is à la mode. So let me start by saying that the first model I will describe is a model which is the most intuitive, and it's the only one which never works. But since it is used actually in many codes, and I will not give names today, but they will recognize themselves, it's a model where you say that the average of the reaction rate is the reaction rate of the average. So you take the Arrhenius form, and everywhere here you put the average on top of it, and bing, here you go. That's what I call the no model. This model doesn't work, and I just want you to realize why. The reason why this model doesn't work is that it's basically trying to ignore that we don't have the resolution in LES or in WANS to capture a flame. A flame is typically 0.1 millimeter, while our mesh is like at least 1 millimeter, maybe 0.5. So we are far, far from that. So if you look at the field of the average quantities, you have one cell where you have 0, one cell where you have the flame, so C might be 0.4, and one cell where you have 1. So obviously, if you try to apply an Arrhenius scheme on that, you will have 0, something, and 0. You are not going to propagate any flame with that. okay? It's just no way. So we could use a model like that if we would not average, but not if we average. Now, another way to realize where the problem is to look at these two flames here. I am sitting somewhere in the flame front, not moving, and I look at temperature. Look here, at this case, I have an average of, which is the blue line, and here I have built this signal to have the same average. Okay, so these two things, these two signals, these 2 points have the same mean temperature. But obviously, this one has much less reaction rate than this one. Reaction rate occurs only when you have a passage of flame. So here you will have 1, and here you have 1, 2, 3, 4, 5, 6, 7, okay? So here the mean reaction rate will be much more than the mean reaction rate here. So it's impossible that the mean reaction rate is linked to the formula which includes only the mean temperature. It's not going to work. Okay? And so this formulation cannot be used in a real code. Now, the problem, of course, comes from this. Okay? If you want to take the average of an expression like this, you cannot just go there and put the average inside. And if you talk to a mathematician, he will tell you, why don't you use Taylor expansion? Okay, then for those of you who love mathematics, you can start doing expansions of this thing, and you end up with a very complicated expression where the first term is actually the no-model term, where you plug the mean directly in the expression, and then you see there are corrections here. And the problem of combustion, that's a philosophical problem actually, is that most of the action takes place at the small scales. That means in this expression, this term is larger than this one is larger than that one, etc., etc. In other words, the corrections are larger than the first term. And so this model also is almost never used, except maybe in certain applications, but very rarely. So it's not the model I would recommend. So let me go to the model which works, which again is a strange model. It was invented by a guy called Spaulding, one of the first guys who created CFD codes and started selling them. That was a code called Phoenix. You were not born, but he's the initiator actually of this whole business of CFD codes. So what Spaulding was saying is saying, okay, I need a model for the mean reaction rate. Well, obviously, if this is a flame in this zone here, there is no reaction because or the temperature theta is 0. It's always cold, so there is never a flame here. And if I go in the burn gases here, it's the same thing because the temperature is always equal to unity, so all the fuel is gone, so there is no reaction rate. And the reaction rates are found only in places where the flame passes over the sensor. And if there are more passages, there will be more reaction rate. So Spaulding said, okay, let's build a model which takes that into account. So he said, for the moment, forget about chemistry. Let's just count how many times a flamelet crosses a given location. So this is proportional to the variance of the temperature. So why is it proportional to the variance? Well, the variance is 0 if theta is constant. And if theta starts oscillating, the variance goes up. So it's a good model because it's at least not 0 where it shouldn't be. And then it's exactly like the diffusion model. You say, okay, this is a term. I need to have the right dimensions. So I need a time here. Here I need a density. And here I need a constant because I know that this constant is not going to be constant. But so I can tune it. Now, the eddy breakup time, which is at the denominator, it's the time of the turbulence. You know, when you see that a flame passes in front of you, it's probably because it's carried by vortices. What is the typical time of these vortices if you're doing runs? It's the only time you have. It's K over epsilon. K is the kinetic energy, epsilon the dissipation. So if you have a K epsilon model, you have this quantity. So you put it here. Now, unfortunately, you still don't have the variance of temperature. But again, you go back to the old guys, Bray, Moss, and Libby, and they tell you that if the flame is very thin, you can prove easily that the variance of temperature is just equal to the temperature multiplied by 1 minus the temperature. That's a demo. I think I've put it here. You know, you just suppose that the signal has this telegraphic shape, and you compute the mean temperature, which is TB over TU plus TB. We already did that. And then you compute the IMS of temperature. And when you work it out, you find it's theta multiplied by 1 minus theta. And so the Eddy breakup model, it has different variants today, including one called the Magnuson model, but they all look the same. You take the mean temperature, you multiply it by 1 minus the mean temperature, you divide it by K over epsilon, multiply by density and a constant, and you get a model. And this model, believe it or not, is the most successful model in turbulent premixed combustion, and it's still used in many codes. Now, if you do measurements, because you can measure the mean reaction rate, at least you can measure its shape, you find this shape here. So this is a measurement which is done in an experiment by looking at the flame surface. And you see that it has like some kind of parabolic shape with a peak around 0.5. And this is exactly what the Eddy breakup model is predicting. While if you look at the no model, it would not say that. So you see that there's something funny here in this thing. For a laminar flame, the maximum reaction rate is very close to the burn gases. But when you average all that in a turbulent premix case, the average is peaking at 0.5, you know, which is exactly what the Eddy breakup model is predicting. This is why a lot of people use actually the Eddy breakup model even today. Now, the funny thing about that is that you can ask yourself, so this thing here is supposed to be the average of this thing here, but I don't recognize any of my constants here. Well, they are gone. All of them are in the constant. The fuel type, the occurrence ratio, whatever, everything is gone here. So it cannot be a very predictive model. If you know the answer, it's an easy model to use. If you don't know the answer, it's tough. So the Eddy breakup model contains everything which you had to throw away to be able to build a model which works. And again, I told you already, in the combustion world, you don't want to be a perfectionist, and you have many constants which are actually not constants, but that's the only way to make this thing go. So at this point, I would like to open a small parenthesis on what we call the ultimate model. There is a model which would work all the time, and that's the PDF model. So that's the probability density functions. I just want to remind you of what this thing is by taking a simpler example that we can do right here in this class. You know, we could take this person and ask him what's his size, and then we would put a +1 at his size. Then we'll take his neighbor, and we'll do that, and we can build an histogram of the sizes of the people in this room. Okay, if we do that all over campus, we're going to have a lot of people, and we can start making that into a continuous description of the size of people as a function of the size. And that will bring us to a situation where we have this histogram, and if we want to compute the average size of the people, we just need to put this formula, you know. We count how many people have a given size, and we can express it like this. So the average size of people on the campus is linked to the probability of having this type of size multiplied by the size. Now, this is something which can be extended to continuous data, so you can build this black curve here, which is normalized so that its integral is equal to 1, and P of S is the probability of having size S, okay? That's the PDF of the size. Now, once you have the PDF of something, you have a lot of information on it. You can, for example, compute, if you have the PDF of temperature, the reaction rate associated to that. The associated reaction rate for a PDF P of theta would be the integral of P of theta omega dot d theta. So if I give you the PDF, you're good. You can compute the mean reaction rate. And so there's been a lot of developments. Actually, even in Fluent today, you can still find a PDF model because people were quite excited about that. And it's true that it's a good solution. Unfortunately, the problem is that we have just transferred our difficulty from a place where we didn't know the mean reaction rate to a place where we don't know the PDF. Because now the question is, what is the PDF? You might say, oh, the PDF, that's easy to find. It's just a function. Well, we're going to do a small exercise here so that you can see that actually finding a PDF is difficult. Otherwise, everyone would do it, okay? So our problem is to find a PDF. So let's go back to our examples of sizes. if you talk about sizes on the Princeton campus, it has a shape, okay? What's the form of the PDF? Well, who can guess? Because we will have to do that for flames. We have to guess the shape of PDF. So what do you think is the PDF of the sizes of individual on the campus here? It's funny because I've done this joke for 25 years and it keeps working all the time. But no, it's not Gaussian. It's not Gaussian. And there's a good reason for that. You know, Gaussian, actually, everyone knows Gaussian because Gaussian is for some kind of homogeneous population. But in terms of size, as far as I know, it's not a men-only or women-only campus. Okay? So on average, the distribution, the PDF of the sizes of women is Gaussian, and the PDF of the sizes of men is Gaussian, but not the sum of the two. And actually, I found this picture, which was taken a long time ago, to illustrate that. They did it on, really, you know, they asked people to just stand behind their sizes here. And you see, of course, that the women are here, the men are here, and you get two peaks. And so this is not Gaussian. It's something else. It's the addition of two Gaussian shapes. And so you see that, for an example, as simple as that, everyone starts having problems. So if we move now to flames, I can tell you there are discussions everywhere. The other thing I need to mention also at that point is that I've simplified the initial problem by keeping only one temperature as the independent variable. But in a real flame, it's not only temperature, you know, temperature and all the species. So you need to find what we call the joint PDF of all quantities, temperature and all species. So it can be a 10 space, you know, 10-dimension space. So it can become extremely difficult to guess what this PDF would look like. So today, people don't use these things too much, a little bit, but I will show you examples. But it's really not the easiest model to use. Flame surface models are quite popular, especially in the piston engine community. And the flame surface models start from this assumption. They say, we have a flamelet here. And you heard this morning, Moshe told us about the Darius-Landau approximation, saying that the flame speed along the flamelet was constant. So if the flame speed is known, and that's this quantity, the total reaction rate is just equal to the flux per square meter of flame multiplied by the flame surface. We call it the flame surface density because it tells you in a given cell how many square meters of flames you have per cubic meters of volume. And so now, if you have a way to know sigma, you have a model for the mean reaction rate. It's more sophisticated than Eddy breakup because you can plug chemistry here. This you can go into tabulation, you can run Cortera, and you can find SC at all pressures and temperatures if you want. So it's quite a reasonable model. It works only if you're in a flamelet zone. If we go back here to the diagrams of premixed combustion. The main problem is to find the consumption speed and to find the flame surface. Consumption speed, in many cases, we end up saying it is the laminar flame speed. I'll talk about hydrogen Friday. You will see there are exceptions. But for most fuels, when you average the consumption speed along the flame here, you find it's very close to what Darius and Landau said, close to the laminar flame speed. So the main problem is to find the flame surface density. Because the flame surface density is created by turbulence, by a lot of things, and this is where things get difficult. And so there's been quite a few people who work on that. I think Pope, and we did also quite a few things on that. And writing an equation for flame surface density is a pain. Let me show you how these things look. They are quite unpleasant. This is the equation for sigma. It has all kinds of terms. One of them you will recognize. It's the stretch that we discussed yesterday, that Moshe discussed this morning. This is the source term of flame surface. If you stretch the flame, you create flame surface, by definition. But at the same time, you transport the flame surface to another place, okay? And the flame moves itself and changes that. And then, of course, you can have sink terms. You don't always create flame surface. Sometimes, if two flames meet each other, you make some flame surface disappear. So you need to model all that. And there's a long, long story of modeling. I just want to show you one example, which is the coherent flame model used by a lot of groups. Converge, for example, works with that. The equation for sigma looks like this. There is the stretch here, modeled by simply epsilon over k. There is a sink term, there is a diffusion term, and this is what people would code, you know. And you can show that if you suppose that sigma is at equilibrium, you will recover the Eddy breakup model. So it is a good generalization also of the Eddy breakup model. Unfortunately, the problem is that when you go into the literature, you will find, you know, a lot of different formula for the terms in the model, because not everyone agrees on how to do that. So there are so many formula that picking up the right model for you is going to be difficult, but that's it's possible. A word about the G equation. The G equation, it's exactly what we described also with Moshe, is the other way. You suppose that the flame is a thin interface for which you know the flame speed. And then you don't try to do more than that. You will propagate the interface. Unfortunately, numerically, propagating this interface when density is not constant is quite challenging, and very few codes today do that. Again, if you look at the history of turbulent combustion, there has been cycle. There was a cycle with PDFs. There was a cycle with the G equation. The reference here is Norbert Peter's book. But in practice, numerically, it's quite difficult to use. Now, I mentioned yesterday the Thickened flame model for laminar flames. There is actually, it's probably one of the most used models today because it allows to incorporate chemistry directly. So the way it's done, you know, you start from this equation, which is the true equation, and you multiply diffusivity by F, and you divide the reaction rate by F. You can still keep 10 species or 20 species if you want. The nice thing about it is that now the flame thickness is larger by a factor of F, and you can actually resolve the flame fronts much more easily. Instead of having, you know, 2 points in the flame zone, now you can have 20 or 40 or 100, depending, you know, how much you can afford in terms of grid. If you are poor, you will use a large value of F. If you get richer, you can decrease F and get more precise. But at least your code can work. And so this is why so many people use it at the moment. Now, of course, there is a price to pay for that. It's clear that you cannot thicken the flame front and not lose something. If you propagate a flame which is 1 centimeter thick instead of 1 millimeter, something which must happen somewhere. So you have to correct for that. And the way you correct is that you have to introduce what we call an efficiency function. And we measure the efficiency function usually by doing DNS. So you have here an example of a flame which is not thickened, F equal 1, and the same here with F equal 5. And you see that when F equal 5, there is much less surface than here, because it's difficult to wrinkle something which is big. You know, the vortices cannot go into the flame, and you cannot curve something which is big here. So, for example, you see these points here have completely disappeared when you thicken the flame front. So what do? You measure the difference between the two here, and you multiply then in the initial equations, you multiply, let me show you, did I write it down? No, it's not there. Let me go back here. You multiply here the reaction rate by E so that you can make the flame faster. In other words, it has less surface, but you have sped it up so that it is actually burning at the same speed as the initial one. And of course, E now becomes the place where you put all your modeling. But this is what's done today by really, let's say, a very large number of people. One of the reasons being that when you do that, you can still do complex chemistry if you want. Okay, let me finish by something that, you know, I decided to talk about it because I'm sure that the question will come up, which is deep learning. Okay, at the moment, if you read Commercial Flame, you will see deep learning everywhere. I just wanted to talk about that a little bit. You know that the world of mathematics has been traditionally split in two, models and data. Models is, you look at a pendulum, you try to write the Newton, you know, Navier-Stokes, the pendulum equations to predict the frequency. Data is you look at 2,000 pendulum, and then you make some kind of table to recognize that, you know, the length is such, so the frequency will be that much. In other words, when you do data, you don't try to understand the physics behind it. You just want to mimic it. And that's what deep learning is doing. And so in CFD, normally we should not need any of these methods because we have the equations. if you have the Navier-Stokes equations, you can just solve them. And it's much better than trying to guess, what's happening using deep learning. The point is that there are places where we don't have the equations. And typically, this is turbulent combustion or turbulent subgrid scale viscosities. Those are places which are smaller than the grid, where we don't put points, so we don't resolve the equations. And so this is a place where deep learning can be efficient. And so this is what I'm going to show you. Now, it's an example of how we can use deep learning to predict subgrid scale winkling. So you see, this is the LES mesh. So it's a big mesh, about 0.5 millimeter or 1 millimeter. And here you have a flame, the red one. This is the true flame. But of course, you don't see that in your code, in your LES code, because the mesh you have is too coarse. The only thing you know is that somewhere here there must be a flame, okay? Because here you see 0, you see 1, so the flame should be here. And so the question is, can we teach a CNN or a neural network to guess how much winkling there is here compared to what we resolve? In other words, can we predict this thing? Now, there are ways to do that. The first thing is that when we use models, as I've shown you in the previous models for turbulent combustion, we use some kind of theory to predict that, okay, to predict the winkling. We try to predict sigma over S. That's what we call the winkling. By the way, some of you may be confused about that. There's a funny property of surfaces, is that in a given volume, if you have the field of C and you integrate the gradient of C, you find the flame surface. I was surprised also when I saw that, but believe me, it's true. If you take here, you can check that out with a simple example. If you know the field of C in this field here and you make the integral of the gradient of C, you will find sigma. If it's a flat flame, you will find 1. And if it's a corrugated flame, you will find the flame surface. So we'll talk about the surface, and we will measure the surface by the gradient of C. So the gradient of C average is the truth, and the gradient of C average is what the LES model will see. So I just want to show you how you can do that using a CNN. The CNN, the role of the CNN will be that I will give him an LES grid, and I will ask him, what is the subgrid scale winkling? Can you tell me? Of course, the CNN has no idea. You have to teach him how to do that. How do you do that? Well, usually in fluid mechanics, you provide a DNS on which the CNN can learn what's going on. So here you see a typical DNS. So this is the Bunsen burner. You inject turbulence. The flame front is here. And this DNS is very well resolved. On this DNS, we know everything. So this is an example of the animation. You see the fresh gases, the burn gases, and we can measure the flame surface here as much as we want. So I'm going to show you how we train. This is the usual procedure with a CNN, okay? You have a training phase where you teach him what to do. Then you have a testing phase where you verify that it's doing what it should. And then you can apply it in another code. So we have what we call the a priori test. Those are cases where you just test if the model does what it should on one snapshot, for example. And then we do a posteriori test. That means you take your code and you plug the model in the code and you run a long simulation to see if it's doing what you expect. So I'm not going to give you the details of the CNN methodology, okay? It's not a school on AI. I just want you to understand how it works. So the way it works is that you take your DNS and you filter it. So these DNS are big, 500 by 500 by 500. So you filter it exactly like you would in LES. So you do it 100 by 100 by 100 or less than that. And then when you average, you produce an average field, a field of average C, average temperature. And now the CNN must tell you how much winkling there is. To do that, you give him the true answer from the DNS, so that every time he sees this picture, he also sees this one. So after a while, he must be able to predict that without seeing this. Once he is trained, once he has learned how much winkling there is, he should be able to give you the information right away. Well, now, right away, it takes a long time, huh? So let me show you how this works. You have this training phase here, so we give the fully resolved DNS this is the average result. You see that this field has been averaged. So this is the field that will be resolved in our code. And this is the subgrid scale winkling. The subgrid scale winkling is obtained from the DNS, because here, when we take a box, we can look inside and measure the flame surface, and we plot it here. So for example, you see that here, this point of high flame surface is this zone here, because there is a high surface. Okay? And so we give millions of these snapshots to the CNN, literally millions, because we run the code many times, and every time he sees that, he learns, so that after a while, he's able to give us the winkling from the mean field without seeing anything here, because he has learned already, so he knows if he sees a field like this with this type of shape, he knows that the winkling must be like that. Okay? A very important thing about CNN, which is nice actually, is that when he does that, it doesn't look locally at the value of C like what we do in a model. In most models for turbulent combustion, we look only at one point. The CNN doesn't do that. He looks at the whole field in one shot. So he knows, that to find the winkling here, he has to look at the whole field of C. So somehow he guesses in 3D the shape. Again, he's recognizing the cats and the dogs. Somehow he knows that if the shape of the field, this is a cut, but it's 3D. If field like this, then it must mean that there is a lot of winkling. So you teach him that, and then once you have done that, you can test if it works. So for this DNS, we did a specific test. We started actually pulsating this flame by sending a train here. So we took the inlet velocity, brought it up to 20 meters per second, and brought it back down. So that creates a mushroom that you can see here propagating along the flame front. And we measured the flame surface in the DNS, which is here. So you create more flame surface here, and then you go back to the initial shape, okay? It's like you're shaking the flame front. Now, we tried now to see if the network was able to capture that. And indeed, it's doing rather well. So after filtering and applying this methodology, this is what we obtain. This is a function of space here going from the inlet to the outlet. And you see here the DNS with the dots. And the line here is the CNN prediction. And this is the prediction obtained with the Thickened flame model or with the Eddy breakup model, let's say with other models. And you see that the CNN is doing amazingly well, okay? The CNN is capturing the shape and the subgrid scale winkling extremely well, which is what you always observe with CNN at that point. And then you can also go one more way, and then you can say, okay, let's run now directly the CNN model in the code. Instead of running a turbulent combustion model, we can directly run the CNN. Now, just a word about that. If you want to use AI in a CFD code, today, you better stop CFD and start computer science, okay? Because everything which is neural network lives on GPUs, okay? Everything which is CFD, well, not everything, most of it lives on CPUs. And if you want to run a CNN in your code, you need to couple GPUs and CPUs, which is what we did, but not me, okay? It's a pain. You need to couple, you need to find a machine on which you constantly exchange information. So you send the average temperature to the CNN, and the CNN sends you back the winkling. That's easy to say, but to make it efficiently, it's really painful. And so when you do that, you can do, for example, a flame like this one, where you pulsate the inlet here, and this is what the DNS gives, this is what the classical model gives, and this is what the CNN gives. And when you compare, we can actually prove that the CNN is doing better. When you look at the statistics, the CNN is here, it's doing better than the other models. So you might say, okay, great, so it works. Actually, let me jump that. Actually, it may work, but what happened after this talk, this was done a year ago, we used the same CNN on a completely different configuration, and then it was completely way out, okay? And that's where we hit the main problem of neural networks, is that they are pretty good in the configuration where you teach them, and they are not pretty good when you change configuration because they have learned something specific, and they have no way to extend it. They know how to interpolate, they don't know how to extrapolate. And so the answer of the CNN guys at my lab were to say, oh, well, you just have to learn on the new configuration. I say, okay, I have to learn on every configuration. So that's not a model. In other words, if you do DNS of every configuration, then you can do a turbulent combustion model. But if I have a DNS of everything, I don't need a model. So I think at the moment, the big problem with CNN is really the fact that when you do it on one configuration, you are not sure that it will work on another one. Unlike theory, when you build theory for a model, you know how it works, which is actually the other problem of CNN. Since we don't know how they work, they raise a big problem for industry, because if you want to certify anything using a CNN or AI in general, since you don't know how it works, you don't know if it can fail. And so people are not so happy about that. So I know that you will find a lot of papers, a lot of contracts today on neural networks, but be careful. It is not that simple. It's a complicated story. Let me see. Yeah, we have time to start discussing the next topics, and maybe we'll come back for questions after this talk. Since many of you are actually doing CFD, and for the others who don't do CFD but would like to be able to criticize their colleagues, I'd like to spend now maybe half an hour or a little bit more on CFD, specifically. So, you know that one of the problems of CFD is that either you believe in it or you don't believe in it, but there are places where CFD has been used so badly that people don't even want to use them. For example, in France, you cannot predict the safety of industrial systems using CFD. They won't listen to you because they know that it's not working, well, at least their conclusion. At the same time, also, we see that more and more people expect much more from CFD. They expect CFD to predict the noise. They expect CFD to do ignition, quenching, instabilities, a lot of other things. And so one of the problems we have now is not only we need to do better models, but as you will see now, we need to go to large D simulation, which means we need to change the code. Because it's not sufficient to put a model in a code to do LES. You need a good code to do that. Okay, so I'm going just to remind you why we want to do LES or DNS, and then I will tell you what is needed in terms of physics, and then what is needed in terms of numerical methods. We talk only about turbulent codes, okay? 3D, turbulent simulations. I'm not talking about Cortera or Chemkin or all these things. Those things are easy. The main difficulty is really to be able to do something in 3D and turbulent flames. And we'll talk only about the full compressible equations, but everything I'm going to say could be used also for simpler formulation, like a low Mach number. So there will be acoustics, and I will need to talk a little bit about acoustics. We'll get you ready for tomorrow. I don't know how many people here have studied acoustics. Who has already had a course on acoustics? Okay, not so bad. Sorry for the others, you will have to learn a little bit about acoustics. So we have shown the equations. I just want to remind you that we're going to solve all these equations, energy, species. We have all the terms for that. And that the main problem that we have is that we need to do that in a turbulent flow, that we don't have enough points to do all that with precision. So for a long time, I've already shown you this, we have done this method where we try to average, and today, your generation, you're going to have to go to LES. The difference between LES or DNS here on the left and average fields is enormous. You have here on the right side the average field of temperature, and here you have the instantaneous field, and you see, of course, that there are big differences. And if you want to be precise, obviously, especially you should not satisfy yourself by looking at the mean. I mean, you want to look at the instantaneous field. Now, no combustion here. This is just backward-facing step flow. I want you to have a feeling for what that really means. This is the Wands computation of the backward-facing step flow. The flow is coming from the left. You have a big recirculation zone. This is a Wands computation. It's not moving, okay? It's going to be like that forever. It's supposed to be the average field of velocity. Now, this is LES of the same flow with the same code, except now we have activated LES. Okay, you see that right away, we have vortices here. This thing is moving, and if we average it, we should recover the experiment, and not, I think we had discussion yesterday about that, not the runs. We should recover the runs if the runs is exact, okay? But like, since most runs computations are not that good, it's better to compare with an experiment. So let me show you here an example of a tube, which is first initialized with a run simulation, but then we turn on LES. So this is a simple turbulent tube, and you see that when LES is activated, the tube, of course, becomes unsteady. It starts moving. And we resolve turbulence here, and unfortunately, the cost also increases, as I said, by a factor of 100 to 1,000 compared to runs. But it's much more precise. The important thing about that when we move to this kind of simulation is that in terms of needs, it's really not the same. If you do runs, this is the result of the runs computation. You don't need a lot of points. Look at the gradients here. There is no gradient in this direction, so you don't need points. And in this direction, if you put maybe 20 points, you're good. I mean, so with 40 points in 2D, you could compute this flow. So that's cheap. That's why it goes so well and so fast. But if you do LES, it's not the same now. You have to resolve the unsteady structures, which can be pretty small. And they can go in any direction. So you need to put a grid which is regular and which is small enough to capture all the details. And that's going to be already hundreds of thousands of points. So this is why the price is going to increase. And then, of course, you have to do it over time. Okay? So it's going to be hundreds of thousands of iterations. So right away, you understand why the cost will be much more. The other thing also with, which is not so nice about runs is that runs is actually hiding what's going on. If you take a flame like this one, where you see here the average field, but you actually go to LES and slow it down, right away you see what's behind this average field. And what is behind it is all these structures, all these eddies. And you see that they are not regular. And right away, you understand that if you want to go into the physics of this flame, it's going to be much better to be able to compute those things rather than only having access to the mean. So, commercial flame, I think we don't receive any papers on runs anymore, okay? It's been maybe one a year or something. It's gone. So for your generation, don't do runs. Everyone wants to go to LES, or if you're rich enough, you can even do DNS. So the question I want to discuss now is, how do you do that? What do you have to do if you want to write or use or develop an LES or a DNS code? So I want to talk first about the physical model that some additional models that you need to put into those codes. The first one, quite often, is not that intuitive, is that the fact that in an LES code, turbulence is not just K and epsilon, okay? Turbulence has to be introduced and resolved. So for example, if you do a simulation of a blade and you do it with LES, you need to introduce turbulence at the inlet by resolving it. That means you need to create a turbulent field, which is a funny business that's going to use a lot of PhDs, actually. So this is another that makes very nice pictures. We introduce turbulence here on the left. And you need methods to do that. Here we're looking at the vorticity, and the results will be completely controlled by the quality of the turbulence that you inject here. So you'd better do a good job in injecting turbulence, which, by the way, leads you to the question of what is turbulence, again, and that's a tough one. So how do you do that? You need two things in a code to inject turbulence. You need to know the signals that you want to inject, U, V, W as a function of time, okay? And those are imposed using a spectrum usually, a turbulent spectrum. But then there's a numerical problem. You need to work on boundary conditions. And boundary conditions become complicated. Normally in a boundary condition, you say U equal 10 meters per second. That's over now. Now you need to specify at each point an unsteady signal matching, your turbulence conditions. And that's a big job. The reference papers there is this one, actually. We wrote that a long time ago. but it's still quite used, and that this method is called NSCBC. I just want to give you a few examples of what that gives. So to do that, I need to go back a little bit to acoustics. So what is acoustics? Okay, that's, you've seen this equation this morning 10 times with Moshe. This is the Euler equations, okay? Everyone knows that. You can do things on that, you know, you can say, okay, let's suppose we are in this room, there is no mean velocity, except if someone open air conditioning, you know. The mean pressure is 1 bar. And when I'm talking, I'm creating small perturbation of velocities and small perturbation of pressure. If I suppose that P prime over P0 is small and U prime over the sound speed is small, I can plug that here. And I can also suppose, with good accuracy, that those perturbations are isentropic. So, you know, remember isentropy, you know, it says that P is proportional to rho to the power gamma, which means that the P prime over P is gamma rho prime over rho. And this thing here, gamma P over rho, is nothing else than the sound speed, so that the perturbation of pressure in this room will be connected to a perturbation of density with the sound speed square in the middle. So you plug that into this equation and you find what we call the linearized Euler equations, which are the baseline equations to do acoustics. So these equations show you how to compute the propagation of a pressure perturbation or a velocity perturbation. Exactly like those equations drive actually the propagation of sound here in this room when I'm talking. So you can combine these two equations to obtain what we call the famous wave equation. And I've written this wave equation here in 1D. So you see it's the second derivative of P prime versus T versus second derivative versus X and 1C squared in front of it. This equation has a very simple solution. Well, two solutions actually. One solution, which is a wave traveling right. So when I'm talking to you, sound's going that way. But there's also the same thing when traveling left, just by having U prime and P prime in a ratio of rho C with a minus, you go left. If you put P prime equal U prime over rho C with a plus, you go right. Okay, so just to give you an idea, if this is the x-axis, I take this room, for example. I create a perturbation of pressure and of velocity such that they are in a ratio of rho C 0. That will lead to a wave propagating to the right side, okay, at the sound speed. So you know where it will be. After a time t, it will have moved by a distance ct, okay? Quite easy, huh? You can do it the other way. The other way means you will put a perturbation where P prime and U prime are opposite, and then this thing will travel in the other direction, okay, at sound speed C0. So the general solution, like in any, again, I'm going fast here, but I'm sure you remember that. For a linear problem, the solution is a combination of solutions. So here there's only two solutions, so you can combine them. So any wave will be the superposition of something going right and something going left. Like in this room, when I'm talking, one wave goes this way, another one goes that way. Now, where things get funny is that the wave going that way will reflect on the wall and come back. The one going this way will reflect and come back, and then acoustics become interesting. And we'll talk about that tomorrow more when we talk about combustion stabilities. So these waves exist everywhere, in all fluids. Even so, a lot of you are talking about incompressible fluids without waves. It's not true. I mean, even in water, you have sound, okay? This is how you found submarines. So if it is everywhere in real fluids, it's also everywhere in all codes, including all compressible codes. So if you're using Fluent, Converge, whatever, if it's a good code, it includes acoustic waves, and they must be there. And so the problem is that we're going to have to think about what that means. I just want to start by one more step linked to the equations themselves. That's the two equations I wrote. There's a very interesting exercise. Actually, this is also in the book by Landau. This morning, Moshe mentioned Landau. And that's how you derive the acoustic energy. So the acoustic energy, you can multiply the first equation here by P prime, the second one by U prime, and you sum them, okay? If you do that, you arrive to this equation. d over dt of this positive quantity here, U prime is the perturbation of velocity, P prime is the perturbation of pressure. So the ddt of this guy here is only linked to the divergence of P prime, U prime. And this is actually what we call the acoustic energy And this is the acoustic flux. And this equation tells you that in any fluid, the acoustic energy changes when there is a flux here, P prime, U prime. Otherwise, it doesn't change, okay? So again, you're going to ask, where is he going? So don't, just wait. If we integrate now this equation over the whole domain of computation that you guys are using, you're computing a combustion chamber, for example, you see that it means really that dE dt, the total energy in your box, plus the divergence of the flux equals 0. And E here is the total acoustic energy that should be in your computational domain, and F is the flux on all boundaries. So let's take a combustion chamber. And many of you actually are probably doing that. If you take a combustion chamber, this is where your code is used, and here you have an inlet, here you have an outlet. What most people do is at the inlet, they impose the velocity. They say U equal 10 meters per second. So U cannot change. If U cannot change, U prime has to be 0 because it cannot change. So that means here that the flux P prime, U prime, here is 0. At the outlet, a lot of us actually like to have P prime equals 0. We want to impose pressure equal 1 bar. So if pressure equal 1 bar, P prime equals 0. So the flux also is 0 here. So you see that the flux in this equation is 0 everywhere because it's also 0 on the walls. On the walls, you have U equal 0. So U prime obviously is 0. U prime cannot change on the walls. So since the fluxes are 0, it means that the first term here must be 0. So dE dt is 0, E is constant. So the acoustic energy which is in your box can never go away. So I've just demonstrated that in a compressible code you can never converge. Because, with these boundary conditions, because the acoustic energy which will be there at the initial time will keep bouncing all over the place so that you will never go to steady state. And you will tell me that in Fluent that's not the case. We'll explain in a few minutes why. In a code, there are two things I've neglected. One thing I've neglected is the viscous dissipation in my demonstration. If I would have kept viscosity, I would have had a small term here, mu multiplied by some term. But in a LES code or in a ONCE code, you get much more problematic terms. You have the turbulent viscosity, which would be there, and the artificial viscosity, which would be there. And these terms would kill the acoustic energy, and that bring the code to convergence, but for the bad reason. And in LES code, we don't want to do that. We want to keep the acoustic energy where it should be. So in other words, in the real world, the energy is dissipated because there is a flux here. How do we know there is a flux in a combustion chamber? Just because if you're sitting outside, you can hear it, okay? Obviously. So if there would be no flux, you wouldn't hear anything. So that means when we say U prime equals 0 or P prime equals 0, this is not sufficient. We need to do better than that. This is where we need a method for boundary conditions. And also, we know that in many of these codes, these two terms here are much too large, and they kill the acoustic energy for the wrong reason. So let me take an example, because that's probably easier for you to understand. If you take a compressible code in a tube, where you impose the velocity at the inlet and you impose the pressure at the outlet. And you put at the initial time some noise here. I have decided to put a wave propagating to the right side. So this is the typical example. Many of you will do actually if you do 1D flames in a compressible code. You would put a flame here. The flame would make a little bit of noise initially because it's not exactly the right flame. And this noise will propagate to the right side. I want to show you what happens when we change the boundary condition at the outlet or at the inlet. So let's begin by the first case where we really impose pressure at the outlet and we really impose velocity at the inlet. When we do that, normally the acoustic equation tells us that the acoustic energy should never go away. So this looks a little bit abstract, but if you look at the simulation, you're going to see what that means. So this is the velocity perturbation, 0, there's a bump, 0, pressure. You will see now this thing going at the sound speed towards the outlet. And since the outlet is reflecting, because the pressure is constant, the wave will come back. It will come back, and then when it will arrive here at the inlet, since it cannot get out, because velocity is 0, it will also be reflected, and this thing can go on forever. As you see here, now we have a wave bouncing at the inlet and at the outlet, and if the code is good, if it's not dissipative, this will keep forever. It actually does keep forever if you get a good code. Now, if you change the outlet boundary condition, and now you use this characteristic boundary condition I have described. I did not describe, actually, it's a complicated method. It's a method where you manipulate the acoustic waves here so that you identify what's going in, what's going out, and you can let the waves go out by the outlet. This is what you obtain. Blim, okay? As soon as the wave reaches the outlet, it goes out. So that's what we call non-reflecting boundary conditions. And it's, for flames, extremely important. Because in the flame, if you don't let the acoustic waves leave the domain, they come back, they interact with the flame, they make more acoustics, and then you're in trouble. So you see that if you want to write an LES code, you're going to need to worry about acoustic boundary conditions. And this is why my paper is cited 4,000 times. By the way, if you want to be cited, you see, don't write results, don't write papers on your results. No one really cares. Write papers on the methods which allowed you to get the results. Because those papers are cited because they're useful for the readers. When you write a big paper saying, I did this wonderful computation, people say, yeah, why do I care? But if you tell them how to do the same, that they are more interested. That's a key element if you want to do LES. You need these boundary conditions. Okay. I want to finish by talking a little bit about the models before the break here. I just want to stick to the model you use for the subgrid scale turbulent viscosity. You know, that's the model you need for the velocity. Here on the right-hand side, you need to model this unclosed term, and usually we do that with a turbulent viscosity. And if you open the sources of Wan's code or the sources of an LES code, they are exactly the same model. They use the same formulation here. They replace what they don't know here by a turbulent viscosity. So where is the difference? Well, the difference is only in the expression of the turbulent viscosity. If you go in a Wan's code, you're using the K epsilon model. So you say that nu t equal K square over epsilon. If you're using an LES code, you're using a nu t, which is usually, for example, with Smagorinsky, expressed like this. This is the size of the cell, and this is the tensor of velocity. But this is the only difference. So the code itself doesn't know the difference between the rest. So that leads to a confusion in the mind of a lot of people that they believe that it would be enough to go in those sources and to replace this expression by this one so that they can transform their Wan's code into an LES code, okay? But that's not true, because the problem is if you want to do LES, it's not only the model that you need to change. You need to change the accuracy and the numerical properties of the code. And that's what we will discuss after the break, because I think it's a good time for a break. Any question or comment? Yes?
So you showed the neural network problems with that, right? Because it can only apply for a particular configuration, particular mixing rate, injection, whatever. The problem with neural networks is that they store data in an unreadable unit table, so you can't read what it has learned. That is why you cannot apply to other cases.
Well, it's not that you cannot read, it's that you don't understand what they really did.
You can be understood by humans, right?
Yeah.
Yeah. But what if, are there any papers which use like fuzzy modeling or combine anyway with the neural network?
Yeah.
That you can read the data?
It's a huge field. I mean, people today try to build network models where you can understand what they do, which would be what we would need, okay? But that's quite difficult to do. But again, that's the key problem. If we would understand how they do it, we would know if we can use it for a spherical flame or for a planar flame or what. For example, here, they have learned on a flat flame. The Bunsen flame was flat. Is that the reason why they fail on a spherical flame? You don't know, because you don't know what they do, really. And, but maybe, maybe people will find ways to do that. But then the question is, if I change the fuel, if I change the The pressure, what should I do? You don't really know. And so it's a problem, yeah.
For asking another question on the same
I would expect that, yeah.
But you said you have the problem of forgetfulness and neural nets, right? You cannot apply it to another condition. You don't have like a general model. But then you can always have run it on a small case, because DNS is like you have some kind of homogeneous or ahomogeneous turbulence. You can apply it on a small case, and then you can have like a repository of neural nets which are easy to share, right? And then you can plug that on a turbulence model when you're doing LES. So
how many DNS will need to be done in this repository?
So for example, you're doing like a backstep, or you're doing a jet model. So you can have, say if you have 10 models, 10 neural nets, can you do what people are doing, something like that?
Yeah, you know, when my student started working on that, the first month he said that, then the second month he needed another, and then another, and then you end up with 10 or 20. The problem is that you don't know how many DNS you will need. On the paper, you're right. You don't need only turbulent flames. You need to teach him flat flames, spherical laminar flames, Bunsen flames, swirl flames. There are so many possibilities that on the paper, yeah, you're right. On the paper, normally, if he learns everything, he will recognize everything. But the question is, how many DNS will we need to do that, to go to that?
So you're saying when you have a real combustion problem and you're simulating, say, something like a swirling flow, you have many kinds of...
no, it's right, you're right, you're right. No, but no, I agree. On the paper, what you say is perfectly logic. It's just that in practice, when we try to do it, we started asking ourselves, how many DNS will we have to do? And for the moment, we haven't found a good way. I got actually one student is in this course. We got 2 or 3 guys doing that full time, and we never seem to have enough databases to teach the CNN. And then there's the problem of combustion. You change the fuel, you have to redo everything. Or worse than that, you just change the composition. You had 50% CH4, 50% H2. Now you have 60 and 40. Do you have to redo everything? Wow, the dimension is enormous. It's like tabulations. I will talk about tabulations too. The domain to tabulate is enormous. It would be better, again, it would be better to have a smart model. Okay?
But I guess the rest of the neural net industry is also suffering with the same issue.
I know. It's not simple. Yes? There are many ways. We have generators of turbulence which are applied directly on the patch, or we can use what we call precursor simulations. So that's another tube which is turbulent and where we read the data in each plane. But the problem is that you need to run the 2 at the same time, and that can make things complicated. Yes?
The acoustic energy is pretty small as compared to the energy associated with the fluid flow. And I understand that even a very small amount of energy, if it's not dissipated correctly, can make big differences in the flame. Are there rules where you can, what I'm really getting at is if you have very high order numerics, which are not very dissipating, the new A which you showed is actually going to be small as compared to something like second order. So it will be a bigger problem if you don't have
Yeah, you can hope that the acoustic energy will remain small. Unfortunately, quite often it's not, because when you initialize a code, usually you are so far from the final solution that it makes a big wave. And so if this wave is not evacuated in the right way, usually it stays there for a long time and it makes your life difficult. And of course, if we would know the solution at the initial time, we would not need the CFD, okay? So we usually don't know how to initialize those flows. If you have a flame, for example, usually when the flame starts, it generates a big wave. And so our experience is that we need to be able to handle this wave. Yeah.
Well, runs is usually very off, but a lot of the faults that we have are heritage from personal experience. But like it claims that even defining a Reynolds number is tricky because it's also transient, right? If you have ignition, then there's laminarization.
Yeah.
Would it make sense to like come up with a new theory of like characterizing flames, like let's say a transient Reynolds number?
Yeah, you can, but the trend today is more to go to LES to not have to care about that. That's the lazy way, let's say. Also because, you know, the old guys before you, we have tried a lot of things, and none of them worked as well as going to LES or DNS. So I think a lot of professors have given up on trying to make a breakthrough different than just putting points there. This is why we don't see, you know, almost any paper on RANS anymore. Even actually on Reynolds stress models, which are much better, but they're so complicated to use, and it's just not worth it. Well, if you're doing aircraft simulation, you still use RANS, okay? Because there, the Reynolds number is so large that LES will not work. But for combustion, where we can tackle the problem with LES, I think it's really the way to go. Okay, we go for a coffee. We come back in 10 minutes. Okay, let's go back to work. So we'll have a short break in the world of combustion now to talk about numerical methods. So I suspect many of you have already followed a course on numerical methods. So I'll try to keep it short, but there are a few things you really need to understand if you want to do CFD and LES, and also if you want, as I said before, to understand what the limits are when you look at the results of your colleagues and they tell you, I've computed it, so it's right. I guess in many cases, I've computed it, so it's not right. So to do that, I need to start discussing the numerical methods and to talk about waves. It's another field probably that not all of you have touched yet, but you've seen that acoustics actually waves, but you have other waves in fluid mechanics, okay? You can have entropy waves if you have a hot spot propagating in a flow, a hot temperature, a hot zone of high temperature. You can have vorticity wave. And that's, of course, for us in turbulence, vorticity waves are the most important. They are the turbulence, really. They are the things that we want to compute. So we need to be able to compare them and to propagate them in the right way. So let's start by talking about the vorticity waves. Vorticity waves means turbulence. So what is turbulence? We all know what turbulence is. I've shown you a picture. I just want here to remind you again of a very important thing, which is obvious for people doing aircraft, but combustion people, they try to forget that. Everything depends on the Reynolds number, okay, in the real world. Velocity multiplied by size divided by nu. In a gas turbine engine, this can be millions. Usually people say, oh, it's a million, and then they forget about it. Well, you should not forget about it, because when this guy goes up, your life becomes miserable. So when the Reynolds number goes up, the size of the smallest eddies in a combustion chamber goes down. Okay? That's the first thing you need to remember, is that when you have large Reynolds number, you have very small eddies, and that's going to be a problem. So in a flow like this, which is a swirled combustion chamber, here they're talking about 2.3 billion cells, so you see it's a reasonably large computation. The largest eddy here is the integral scale. That's the place where the flow recirculates. But then you have very small eddies here on top. This one, for example, and this one you can prove by theoretical arguments that it is this one divided by the Reynolds number to the power 3/4 or something like this. Let's say it goes down when the Reynolds goes up. And so you see that every time someone increases your Reynolds number, it's not changing this guy, but it's changing that one. This one gets smaller and smaller. And so you need more and more points. And the number of points increases like Reynolds to the 3/4 to the power 3, because you get 3 directions. So it's like Reynolds to 2 point something. So when you go from Reynolds equal 1,000 to 5,000, it's not a detail, even so you don't see it. So that's a very nice Italian movie actually showing a non-reacting flow in a tube. It's the same tube, and the only difference is that here the Reynolds tau, don't forget about what that means, it's a Reynolds number, 150, and here it's 1,000. And so you see, of course, the big eddies are the same, but look now at the small eddies. The smallest eddies are the one you see here. Look at the difference in size, okay? And if you run this thing, you will see that, of course, when Reynolds number equal 1,000, there are lots of small eddies here. And so the mesh here is amazingly larger than this one, okay? So really, the problem when we do simulations, and when you talk to your PhD colleague telling you I'm doing all this wonderful LES of my chambers, what is your Reynolds number? If the Reynolds number is high, then probably you're not doing what you should. Now, this is an example of the number of points that you would need to resolve a tube. When the flow is laminar, you would need a few in each direction, but when the bulk viscosity goes up, the Reynolds number goes up. As you have seen in the previous movie, you end up needed, if you would resolve everything, 10 to the power 12 points just in this tube, if we would want to do DNS. So you cannot do DNS. We need to do LES, and we need to, to be able to run our code. Now, this was always true, okay, that we needed something to do that, to fix this problem. And the way we fixed it is that we used two models. In practice, I think there were PhD students in those days, and they came back to their professors and say, well, I have a solution, it's dirty, but at least it works. So the two dirty solution is the turbulent viscosity and the numerical viscosity. If you have a code, and you try to compute a high Reynolds number flow, the code will explode if it's a good code. Why? Because it will see that some vortices are so small that he has to resolve them on one point, and then blib. If it's a good code, it will just not converge. If you want to make it work, you have to use these two tricks, the turbulent viscosity and the numerical viscosity. So let me explain where these things come from. Yeah, some of you may not be used to Navier-Stokes equation, you're just coding them, but you have to get into them, to understand what's going on. That's the momentum equation. This term here is your friend. It's the viscous term. It's the term which prevents eddies to become too small, because if viscosity is large, when you have a big vortex, it will go away. If this term is useful for us, it's because also it's a linear term. If you multiply this velocities by 2, you multiply this term by 2. Great. Now, the problem is that this term has to fight the guy on the other side here. This guy is not your friend. Why not? Because it's a product. Forget rho for the moment. There's a product here, ui, uj, which is a nonlinear term. I don't know how many people here have studied chaos, but you know that linear equations don't do anything to you. But if you take any equations like y prime equal 2y squared minus y cubed, this thing can get crazy because it leads to chaos. Chaos leads to turbulence. And so in this equation, you have to understand that turbulence comes from this guy. If this term would not be there, you would not have to care about turbulence. Everything would be linear, like people solving the heat equation, dt dt equal alpha Laplacian of t. That's great. No turbulence, okay? But for the flow, this guy hates you. And the way it works is that this guy creates the turbulence, and this guy dissipates it. And the ratio between the two is the Reynolds number. So when the Reynolds number is large, you have a lot of people who are not really friendly, and just one guy trying to help you by dissipating the energy. And so this is a tough fight. So how do you handle that in practice? Well, in practice, what people said, they said, okay, this is the instantaneous equation. I'm going to redo what I did yesterday here. So let's suppose we average, and then we end up with this term here. And so this term, which is unclosed, we close it with a viscosity, which looks like the laminar viscosity, so that we can actually increase the laminar viscosity by the turbulent viscosity. So that what is really coded now is this thing. On the right-hand side, you have nu plus nu t. Okay? So you add a viscosity. In other words, you make the Reynolds number go down because you increase the term which dissipates energy. That's one way to fix the problem. The other solution is, if you look at basic courses on numerical methods, you know that if you're trying to solve this equation, which is really the baseline equation for waves, this is an equation where you propagate a signal f at speed u. If you discretize it this way, with here a centered derivative, this thing blows up right away. I mean, it's unstable. If you remember your courses, this thing is unconditionally unstable. And so the way people fix this problem is that they add a second order term on the right-hand side of the equation, which is fi plus 1 plus fi minus 1 minus 2fi divided by delta x squared, and that fixes the problem. If you take a new a here, which is not too big, you're able to make this equation stable. except that, of course, you're not solving this equation anymore, you're solving that one. Because this expression here is just a discretization of that one. And so now we have added another viscosity. In addition to the turbulent viscosity, we have added a an artificial viscosity to our problem. Now, by the way, many of you are using codes where people say they are not using artificial viscosity because they have upwind schemes. Upwind schemes is a way to stabilize schemes where you, instead of Fi plus 1, here you put Fi minus 1 when U is positive, and that fixes the problem. But again, if you do the Taylor analysis of that, you find out that, again, you have just added here a second order term. So even upwind schemes do introduce numerical viscosity. So at the end, when you integrate all that, you see that now you are going to use a code in which the viscosity will not be the laminar viscosity. It will be the laminar viscosity plus the turbulent viscosity plus the artificial viscosity. So this is numerical, this is modeling, and this is the truth. Now, the problem is that if these things were small, we'd be in good shape. But as you will see, when this is 1, this is 1,000, this is 2,000. So these are not details compared to nu. And they are so big that the Reynolds number of the flow now is extremely low. It is sometimes so low that the flow is laminar. And by the way, I've seen that only a couple of times in my career, but there are students who come back to me and say, I'm solving the Navier-Stokes equations with fluent, for example. The flow is turbulent, but it's not moving. And of course, you say, of course it's not moving because you are computing the mean. But still, the Navier-Stokes equations, which are coded, are the same as the Navier-Stokes equations in nature. So if in nature the flow wants to move because it's unstable, in the code it should move also. Why doesn't it move? I'm computing a wing at Reynolds number equal 1 million and nothing is moving. Well, it's not moving because the nu t and the nu a are so large that in your code, the Reynolds number is not 1 million, it's 200. And at 200, of course, it doesn't move. So it is a laminar flow where maybe the viscosity is a little bit strange. It's not the laminar viscosity, it's a complicated viscosity. But what we've really done is to make this flow laminar, okay? Totally laminar. And that's bad because, of course, if you want to compute turbulence and you are computing a laminar flow, you know that there are many things which you are not going to capture. But that was the truth 50 years ago. The PhD student was able to get his PhD because he got the code running. Okay? Because in those days, there was no choice anyway. So let me give you examples on a log scale here. If you're using a ones code, this is what's happening. You have here 1 for the laminar viscosity. And the turbulent viscosity is usually between 100 to 1,000 times larger. So that when you have such a large turbulent viscosity and you have customers screaming because they don't want to spend too much CPU time, you can also add artificial viscosity. You add upwind schemes to make the scheme stable so that you don't get the code to blow up. I mean, Fluent never blows up normally because it has so much artificial viscosity. And then, since you don't want to wait, you also use implicit time integration, which also adds artificial viscosity. But it's not a problem because you get so much here anyway. So now when you combine all these things, the Reynolds number of your one's computation is below the Reynolds number needed for turbulence. So it's going to be a steady flow. It's going to be very easy to compute, okay? But it's just not the right flow. It's another flow. But still, okay, it works. Now, at the other side of the spectrum, you get the DNS people. That's where I come from. And we never would touch any turbulent viscosity model and never any artificial viscosity model. Yeah? If you talk to people doing DNS, they would use 12th order scheme for space, 3rd or 4th order Runge-Kutta scheme for time integration, things which are perfect. So we will do things perfectly. So if you do DNS, you have here 0 nu t, very small nu a, so that you are computing the right flow. So we are perfect, except we can compute only a box of 0.1 millimeter. That's a small detail. But when we talk to industry, they tell, well, are you sure you cannot do better? So, of course, what we want to do with LES, we want to do something in between. So to do something in between, we want to diminish the turbulent viscosity by using subgrid scales such as Magorinsky. So we have less viscosity so that the flow can be turbulent at least. And the trick is to do that when you decrease this thing should also be decreased, because otherwise you have a problem. So a good LES code should not use upwind schemes and should use a small time step so that the Reynolds number keeps, as large as possible. And this is where things get difficult. For example, Fluent and many other codes, Converge, all these guys, they have done the same thing. They have actually taken their code, they have just replaced the K-epsilon model by Smagorinsky model, but they didn't change that. In other words, here, when you run these codes for LES, this model doesn't play any role. Everything is controlled by these two terms. So when you change the grid, for example, you get a different result. The way to check that out is if you run those codes, you can go in the code and set nu t to 0, and you will find the same result, because it doesn't play a role. Everything is in these terms here. So everything is controlled by the numerical approximations, and that's not what you want. So again, I don't know, one of you asked me if I believed in CFD. I believe in good CFD, okay? But not that. I mean, this is controlled completely by artificial viscosity. So to conclude here, if you want to do LES, you got to be ready to pay, typically 500 times more. Note that for you doesn't make a difference. The way it works, for example, in France, is that the students or the engineers would do one simulation on one processor during one night, or an LES computation on 2,000 processors in one night, okay? It's just more expensive, but it doesn't take more time, okay? It's just that you need a parallel machine to do more computation. And then suppose that you have the CPU power. I'll come back to the CPU tomorrow, or maybe today, I'm not sure. Is it that easy then to write a code which would be precise? And then you will need now to talk about waves. What does it take to write a code which has limited artificial viscosity? To do that, I need to talk about waves. As I said, our problem is to propagate acoustic waves, vorticity wave, entropy waves in a precise way. Here I need to start talking about dissipation and dispersion. So I don't know how many of you took courses on waves, but let me remind you that in the real world, we will say that a gas, for example, is dispersive if the speed at which waves propagate depends on the frequency. Wow, wow, wow. That means, for example, that for sound, it's not. Because for sound waves, a low-frequency wave propagates at the same speed as a high-frequency wave. Otherwise, far away, it would be very difficult to understand people, okay? Now, there are cases where mediums become dispersive, and the speed depends on the wavelength, not for air. Now, dissipative is something else. Dissipation is if you start a wave here with this amplitude, after 100 meters, it will be like this, and then it will go away. And dissipation depends on the frequency. If you live on top of a nightclub, you know that. If you live on top of a nightclub, you hear only boom, 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 which is the low frequency component of the signal. You don't hear the music, but you hear the low frequency. So air is dissipative, not dispersive. So a flow in which there is combustion is dissipative, not dispersive. Now, if we go to the numerical world, we need to respect that. We need to respect these properties. Our code should not be dispersive, and it can be dissipative if the flow is dissipative. That's not bad news. I said bad news, but it puts some requests on the code. So just an example of dissipation and dispersion. That's, for example, a spot of fuel on air. So there's a mixture of air. The flow is periodic, so whatever comes out here comes back here. And supposedly, there should be no dissipation. So this is a good test where this blob here of fuel must propagate, and we come back here exactly like it was. Okay? And we compare two methods, a second-order method and a third-order, fourth-order in space method, which is called TTGC here. So when you do that, you see that the second-order method has problems. You see that the shape is not preserved, and you see black zones here. I will come back to the black zones in a minute. While you see that the third, fourth-order method here is much better. We propagate the signal without any distortion. So if you do LES, you want to do that. There's another reason why you want to do this. This is a species, okay? The nice thing about dispersion is that dispersion can create strange behaviors, like those zones here. Those are negative. Dispersion does that. When you start from a signal which is like this, and if the scheme is dispersive, you start having wiggles, and the wiggles can become negative. Negative for a species is a little bit of a problem, okay? If you have a chemical scheme, imagine if you say the concentration of O2 is minus something, the chemical scheme will not like it. So this will lead to problems. which sometimes some people eliminate by saying yk equal max of yk and 0. So that's called clipping. You know, if it is negative, I put it to 0, but that does not conserve mass, and you don't want to do that. Okay, so I'm not going to give you a long list of all the possibilities because there are things you can do to understand that just by hand. Again, theory. It's not theory of combustion, it's theory of numerical methods. You can study the properties of schemes without having to write a code just by looking at this equation. So this is the propagation at sound speed c of a signal u. It could also be propagation of temperature at the convection velocity. Okay, it's the same. So it's just to show you how a scheme like this reacts when you change the time advancement scheme and the space advancement scheme. So we're going to do that for the moment with the simplest scheme to derive in space, which is ui plus 1 minus ui minus 1 divided by 2 delta x. And we're going to do a 1D problem so that, again, we can do it by hand. We're going to suppose that we're computing the propagation of a sinusoidal signal. So you see here, this could be an acoustic wave, or this could be a vortex. And this thing is, the black line is the solution at t equals 0. So it's v of 0, which is the amplitude, exponential 2jp omega x, which is the pulsation. And this system has an exact solution. We know that in an equation like this, the solution is just to take the signal and move it by ct, okay, without any change. It's just convected, no other effect. So if our code is good, we should obtain this solution here. V of 0, exponential blah blah, x minus ct. So we know the exact solution. So now we can predict what the code would give. So what would a code do? A code would discretize space in little elements of size delta x. And we know that the code also will predict a periodic solution because everything is periodic here. And we will call this solution v of t, that's something we're looking for, exponential, and x becomes I delta x. And then we can plug this expression into the equation. So if we plug the expression here into the scheme that we have here, we arrive here. dv dt, that's the amplitude, equals this expression. And this thing, if we suppose that we have a perfect time advancement for the moment, we have a scheme which has no difficulty with time, we can integrate it by hand to know that v of t would become this thing. And if we plug that in our initial solution, we find the we find the solution which would be given by the code. I didn't have to write the code. I'm just showing that if I have a code which is second order, this is the result which will be given by the code. This looks pretty much like the exact solution, except if I put the two on the same slide, that here you see that the speed at which my code will propagate the signal is not the right speed. Okay, there's a correction here. At this point, I just want to point out right away that this proves that this method will have dispersion. Okay, the initial equation had no dispersion, but this solution has a dispersive error, and we'll quantify that in a second. Before doing that, I just want to point out that here there's still something good, is that the amplitude is the same. So this scheme is not dissipative. If you would use an upwind scheme, this is what you would obtain. In addition to these two terms, which are up there, you would also have here a term which is exponential minus ct something, which would damp the whole signal. So we don't want to do that. We never use upwind schemes when we do LES. We try to avoid them as much as we can because they would completely waste the quality of the solution. So now you see that the speed at which my code will propagate the signal compared to the true speed is this expression. So this expression, you can plot it, and I'm going to plot it like this here as a function of 1 over omega delta x, which is also the wavelength divided by delta x, which is nothing else than the number of points that you can afford to put in your vortex or in your acoustic wave. You see here, for example, if you put 10 points in this vortex, you will have an error of maybe 5%, which is already big, you know. But if you are poor and you have only 4 points in your vortex, you have an error of 40%. So if you're doing LES of combustion in a chamber and your vortex propagates with an error of 40%, you might as well do once, okay, because it's going to be wrong. So all the frequencies will be wrong. I mean, it won't work. So we need to improve on that. Okay. And how do you do that? Well, it's been known in the DNS community for a long time. When you go to high order, it's much better. I've seen someone yesterday using the 6th order scheme that we developed at CTR a long time ago. A 6th order scheme is here, much more precise. A spectral method would almost be on the exact line. So you definitely need high order schemes if you want to do this job. So let me show you what that gives if you write a code. This is a MATLAB code, and you try to propagate one of these signals here. So I've decided to take this shape, and I'm going to advance it in time. I just want you to look at the results. So the cyan color is the exact solution, and the black is the numerical solution. Normally, they should match at all times. The system is periodic, so when the wave comes here, it will come back on the other side. So look at what's happening. You see, by the way, where you see a lot of things. You see first dissipation. You see that we are losing this thing. You see that we are dispersive. We are a little bit too late, the max here. And you see all these wiggles here, these oscillations. If you do DNS and LES, you're going to see some of these things. I will explain them in a minute. So you see that dissipation and dispersion will occur if you're not careful. Let's go to a 2D case. That's really the prototype case for LES. If you're doing a thesis on DNS or LES, you can do the same thing. And the problem here is to look at a vortex. And in a simulation, there are many vortices of all sizes. So we're going to take one and propagate it in a box like this. So here now you have a vortex, a periodic box. The vortex comes out and comes back. It's non-viscous, so the vortex should come back exactly the way it left. So this is a view of the vorticity. So you see the vortex leaving, coming back. We can make it turn 1 time, 2 times, 10 times, and it should remain the same. Again, no dissipation. We don't want this thing to go away. I'm going to show you results obtained with, actually we did it with CFX, we did it with Fluent, we did it with our code, 2nd order, and then we did it with 3rd order scheme. I just want you to look at the results for the moment. For the moment, we're going to do it also with a small CFL number. That means a small time step, if you want. If you want to repeat those tests, actually, you can go to this e-learning website always at Surfax, and there's a long list of description for this test case with a comparison between different codes. And if you do that, you can also send us the results, and we'll put them on this list here so that you can compare. So this is a view of pressure. Why do we plot pressure? In the center of a vortex, you get negative. You get a smaller pressure. This is the exact solution. And you see that after 3 turnover times here, we should be here, and the 2nd order codes are here. That means they are dissipative and they are dispersive. They go too slowly and they lose too much energy. If you put on the same scale the 3rd order scheme, it's right on the solution. So you see there is a huge difference between the 2nd order code and the 3rd order code for a case like this. And if you go to 10 turnover times, this is what you find with 2nd order codes. There's no vortex anymore. So you're doing large eddy simulation without eddies. Okay, so that's not going to work. It's gone completely here. This thing has disappeared. So you cannot use a low order scheme if you want to do large eddy simulation. While if you do it with a 3rd order scheme, which is much more expensive, okay, huh? But you see that there's a huge difference. It's a world of difference. It's not just a small difference. It makes a big difference. Time step, that's another issue. For those of you who are not afraid, I've seen that actually on the poster, but for many DNS on LES, the time steps are between 1 nanosecond and 1 microsecond. That's small. So if you want to compute 1 second, you need 1 billion iterations. It's kind of difficult. So of course, people would like to use implicit time step, implicit time integration so that they can go faster. So in Fluent, for example, you can do that. And I just want to show you what's happening when you use, here, the exact solution. Here, a time step with a CFL of 0.7, 3.5, and here 25. You see that at 25, everything is gone. It makes sense, actually. It's difficult to integrate signals in time with a very long time step because the code cannot guess where the solution will be. I must say 25 is small. Many computations in Fluent are done with 20,000, for the CFL. So there's no way. You cannot do LES with these things. So maybe someone someday is going to find an implicit scheme which works for LES, but today, if you look at the existing schemes, they are all explicit. Okay, just again, not for fun, huh? They are explicit because this is needed for precision. Now, one issue which is very important is that it's relatively easy to write high order schemes when you use IJK codes. You know, I've called them codes the unconfined spaces in shoebox in a rectangular domain. But if you want to do high order schemes for unstructured meshes, it is much more difficult. Okay, if you go beyond third order, it becomes extremely tough. Quite a few people are working on that. Maybe some of you have heard about these methods here: spectral differences, discontinuous Galerkin methods. There are people who try to go to third, fourth, fifth order in space on unstructured meshes, and that's the key issue from the numerical point of view for these codes. Okay, now I want to finish here this part with a fun one, talking about wiggles. We have seen that we need to propagate physical waves and that this is difficult. What I want to show you now is that when we write these codes, we have the physical waves, but unfortunately we have other things which we call Q waves, and then the reference book here in this domain is Vishnevetsky and Bowles. It's what we call the small black book. It's very easy to read. If you do a PhD on numerical methods, please read this one. It's extremely good. And of course, there's the famous book by Tapan Sen Gupta, who is in India, and also wrote a big book on the same topic. So I'm going to do it very slowly and very simply. Our problem is to look at what we call the propagation of wave trains in CFD. What is a wave train? Well, it's this signal, the red signal here. It has an envelope, which is yellow, and the signal itself is oscillating at high frequency. If you put that in your CFD code, strange things happen. So I'm going to do it for you. This is the same code I've shown you before, but as initial conditions, I've chosen this thing. So remember, this is convection from left to right. This is solution at t equals 0. Now you run this thing. Here's what's happening. After a few iterations, the signal is here, and then the signal is there. And you could say, oh, it's great. It's propagating. Except, remember, I told you the speed was from left to right, not from right to left. Okay? So it's propagating in the wrong direction. So it's not even here a question of having the right amplitude. If a vortex starts flowing in the wrong direction in your LES, you're not going to like it. So what's going on here? First thing I did is you go in the code and you said, I coded it wrong. You know, there's a sign which is wrong. But no, actually, this is actually expected, and you can prove it. It has a wavelength here, what I call 2 delta x. That means the signal goes from plus to minus, etc. And it's propagating in the wrong direction. You talk to someone like Sen Gupta, he will laugh at you and say, of course, that's obvious. So I just put here the demo so that you see that it's actually easy to understand. We're trying to solve this equation. Suppose that the signal that we impose at t equals 0 has an envelope v of x, which is the black line. And then, since it is oscillating from point to there, you have to multiply it by -1 to the power I. Okay? That's the shape of the initial curve. You plug that into that with a centered scheme, and you obtain, du dt becomes this, and this thing is discretized this way. You simplify, and you end up with this. dv dt minus c dv dx equals 0. So indeed, in 2 lines, you can prove that the envelope will travel in the wrong direction at the speed c. So there's nothing magical, okay? As soon as you will have wiggles on your signals, they will propagate in the wrong direction. And that's not something you can accept. You can generalize that by computing the speed, the group velocity of any wave trains, and you find indeed that the general formula is coded here. And this analysis allows to show that the world in simulation is split in 2 parts. You have here the number of points that you can afford to put in a vortex. Okay? If you put more than 4 points in each vortex, it may not propagate at the right speed, but it will at least propagate in the right direction. And we call these waves physical waves because at least they have this physical character of going in the right direction. But now if you're not able to do that, and with LES, unfortunately, it happens all the time that we don't have enough points, you will have to handle what we call Q waves. these waves are not sufficiently resolved, they will create wiggles, and these wiggles will propagate in the wrong direction. So the analogy that Vishnevetsky took, and I think it's a good one, is that those are physical waves and those are ghost waves. Okay? Ghost waves, it's exactly like you buy a house and it's haunted. Okay? In this house, you get normal guests, and some of the guests are propagating in the wrong direction. They are ghosts. Okay? So it wouldn't be a problem, you know, if you would think that this ghost would wake up only at night and not worry you. Unfortunately, let me jump here to this result. It's not the case. In most codes, when these ghost waves unfortunately touch a boundary, look at what's happening here, bling, they convert into a physical wave. So when you wake up in the morning, you know, for breakfast, you get people who are real people, and you have people who are ghosts who hit the walls and came back. So then you have a problem, okay? Now you might say, okay, I was stupid when I bought this house. Let me buy a house without wiggles. Okay, this looks like a good house, okay? No wiggles. Unfortunately, those of you who have done some Fourier analysis know that high-frequency components arrive when you have steep gradients. This thing has steep gradients, so when you start running it very rapidly, you will see that behind it, it has these wiggles too, which are propagating as expected in the wrong direction, which is not pleasant. And then when it's gone, you are left here with all these wiggles. So even if you don't see them, it's kind of difficult to avoid them. Now, the other thing is that these things may live with you during the day, and when they, you know, go to sleep, hit the wave, up, they will generate wiggles again. So it's become extremely difficult to know who is a wiggle, who is a ghost, and who is a physical wave. And so the simulation has to be done in a way where you minimize those guys. Now, the way these waves are reflected on the boundaries depend on their frequency. I just want to show you here two fun movies. This is a case where you have enough points, let's say, and this signal is going to touch the boundary. And you see that when it touches the boundary, it creates a little bit of oscillations here. You can see it here, but not too bad, okay? But if you don't have enough points, and that's always the problem with LES, that we don't have enough points to put in the mesh, then you see that it's going to shake much more. This is a higher frequency, so less resolution, and you see now this signal propagating to the left. When we discovered these things like 30 years ago, people did not expect that. We did not realize those things. And one of the problems is that those signals are small compared to the initial signals. So if you're doing DNS, take a look at zoom on pressure and look at these things. I'm sure you will find out that there may be some of these things here. So as a result, that's a paper we did also a long time ago. You have a mechanism by which you can have a wave hitting the outlet, generating a wave which comes back, hitting the inlet, which generates another wave, and this thing can keep going, and your computation is completely, let's say, something you cannot use because it's just polluted by these waves. Now, to control Q waves, there are things you can do. Of course, these Q waves are plus minus oscillations. So if you put artificial viscosity, you're going to kill them, okay? That's why you never see them in front, because they are dissipated. But we don't want to do that. We don't want dissipation. So we have to use better schemes. We have to be careful with speeches. You should never clip. What you do in practice in most good CFD codes to do for LES, when you see those wiggles appear, you just hit them locally with some artificial viscosity. In other words, there's a guard in the house. Every time he sees a ghost, you hit him. You hit only him locally. And normally that should be enough to clean the problem. In practice, when you're going to do codes which have limited dissipation, it's quite likely that you will see those waves. If you don't see them, it's probably that you have too much dissipation. But you have to get used to it. So what it really means, and at that point also I hear a lot of students telling me, I've never seen that. Well, there are good reasons why you would not see that in many codes. This is an example here of the code that we use, or typically, so if you start from this initial condition, after a while, this is what you obtain. You have wiggles, but you also have a signal, okay? Well, if you use a dissipative code like a once code, after one turn over time, no problem, there is no wiggle, okay? Because there is no signal left. So you have to choose. Usually, if you are too dissipative, you are killing the wiggles and your signal. And so if you have a good code, you should be somewhere in between, and you should monitor your wiggles. They are not your enemies, but of course, they can lead to difficulties. Okay, we still have a few minutes. I'm going to jump right. We'll take questions afterwards. Huh? I just want to jump now to the next topic, which is going back to combustion. And that's a topic, I think, which is of interest for many of you, which is, what about chemistry? You know, it's interesting, next room, not far from here, Alison is talking about schemes with 10,000 reactions. And can we take them in a CFD code? I think that's an important question, and I want to discuss that. So, you know what the chemical schemes are, I guess, by now. They look like this. They have constants, A, beta, exponential EA here. These things are given in Chemkin format. You can download them. So there is no problem in finding a scheme. But if you want to run it in 3D, then there's a problem of how do you feed it into a 3D code. So, of course, you remember that H2O2 is a simple scheme. You can fit it on one slide. But if you would go to CH4 air chemistry, then usually just the elements don't fit here, and then there's hundreds of reactions. So what do we do with this thing? We know these schemes, but in practice, we cannot use them in 3D codes. So the main challenge today is how do we fit those schemes in a big CFD code? Now, you forget about the chemist. You are just doing a computing science, and you are writing the code. You know that every additional species is an additional conservation equation, more memory, more work. How many can you really use? Well, it's going to be a problem. You know, if you add more species, you need more memory. If you add more reaction, it's more CPU time. I'm going to list 4 methods to do that, what I call the brute force, in which you just take the scheme and you plug it in your code, whatever the cost is. It's difficult. I will talk about tabulation, I will talk about reduced schemes, and about analytically reduced schemes, which are recent methods, which are probably the future, I believe, today. I will not discuss the G equation, and I will not discuss methods where, like the flame surface density models, because there is no chemistry really there. I will stick to cases where we want to do some combustion. Remember, we call elementary reaction a chemical reaction which really happens, and we will call global reaction a global reaction which does not happen. It's a concatenation of many elementary reactions. So someone like Alison will only talk about elementary reactions, but in a code, quite often, we use this notion of global reaction to simplify the problem. So, again, global reaction for H2O2 flame, that's H2 plus 1/2 O2 gives H2O. Never happens, okay? There's no elementary reaction doing that. If you want a scheme for H2O2, you need to take the full scheme. So let me start with brute force methods. Brute force methods, you talk to Alison, and she gives you a scheme, and you take a scheme in Chemkin format, you plug it into your code. You can do that today. Many codes do that, but the problem is, can you afford to do that? Well, in practice, we do that in DNS code if there are less than 20 to maybe 100 species, even 100 becomes, you know, and usually do that in 2D. In LES code, we never go to more than 20 to 30 species, you know, and not too many reactions, because the work then becomes too big. There is no assumption if you do that, but in practice, you will find it only for a few flames, normally hydrogen, because you can do it. But in most cases, it's too difficult. This is an example of H2O2 DNS with a full scheme in 2D, okay? And look at this thing here. Between this point and this point, there are 500 points of mesh, okay? Because the reaction zone is this green line here, and you can see how thin it is. So it's extremely difficult to use a full scheme in a case like this, and it's only 2D. Now, remember also that that's a question you shouldn't ask to kinetics experts, you know. If you have 10,000 reactions, for each reaction you have 3 constant, so you have 30,000 reactions, 30,000 constants to specify. Then you ask Alison, how many of those do you really know? And she will tell you, if she's honest, 5%. And where did you find the remaining 95%? Well, we guessed them more or less. I'm not joking, but it's almost a joke. They do a lot of comparison with other molecules. Okay? Oh, it looks like this one, it should be like this one. And of course, after that, they do tuning for years, and they know what they should use. But this is this is again only a model. And remember now, you have heard this morning Moshe and me yesterday. How do you validate these models ultimately when you do a flame? You do it on spherical flames. And if you listen carefully, you know that the accuracy of spherical flame measurements for the speed is quite unclear. So you don't want to be too perfectionist about those schemes, because even the full schemes, they are only models at the end of the day. They are not perfect. So you don't want to try to mimic exactly what they say. This is why a lot of people said, okay, I'm not going to go full scheme, I want to do something reasonable. And then you go to tabulation. Tabulation is a method based on, well, I guess Steve Pope is a good reference here, saying that in combustion, all the species are not independent. You know, obviously, for example, in the flame of methane, if methane is going down, then probably CO2 is going up. Huh? You don't have to consider them as independent variables. And probably, if you plot the trajectory of the species, you will find out that many of them lie on what we call a manifold, which is a surface of lower dimensions than the full scheme that you would expect. So, for example, you know, in a turbulent premixed flame, certainly you will not find points here where you have a lot of fuel and a lot of products. Okay? Because if you don't have fuel, then you have products and vice versa. So it's not reasonable to keep all of that. You can probably keep only something much smaller. And probably most of the action will take place on the line here, where there's a lot of fuel and no products, and when there's a lot of products, there's less fuel. So we can describe this system with less variables. And of course, that will simplify our task from a CPU point of view and a memory point of view. Now, the manifold may look strange. That's an example of manifold thing obtained by Matthias here at Stanford, where you have the N2, the CO2, and the CO, and you see that most of the points in DNS here lie on the surface, which does not cover the whole space. Huh? It covers a much smaller space. So the idea is that you should be able to keep our 5 usual variables for Navier-Stokes, and instead of n independent chemical species, you would like to keep maybe 1 or 2 variables, and then all the others can be related to these 2. And that's the principle of tabulation. Usually, most people, not all of them, but most people use, this is where, you know, CO is useful. They use the progress variable C and the mixture fraction as the 2 important variables, and they say everything else can be connected somehow to these 2 variables. Now, it means also that if you run your code, you will run it with only C and Z, and after, doing the post-processing, you can obtain all the other species, because they're supposed to be a function of C and Z. So it makes your life much easier when you run your code. You only have 7 variables, the 5 here plus C and Z. Now, as I said, normally people use C and Z, but the definition of C and Z can become difficult. Sometimes defining what the progress variable is an issue. Most people would use something based on the sum of CO and CO2 in hydrocarbon flames and normalize it that way, but if the flow is not perfectly premixed, then things get more complicated. So I just want to show you how this would work. The main idea would be the following. We would say that the reaction rate in the flame, which depends on everything here, actually, the temperature is missing here, actually is a function of C and Z only, okay? And then there's a second level of assumption, is that this is true also in a big turbulent flow. And there's an additional assumption, which is that the manifold for the laminar flame is the same as the manifold for the turbulent flame, which is also not so clear. And so the way it would work then is the following. You would take a laminar premixed flame, for example. You would measure the link between omega dot and F of C and Z by doing multiple flames at mixture fractions which are different and different level of C. You put that in a table, and when you go to the 3D now, you read C and Z in your DNS or LES, and you just use that as the reaction rate. So you see there's a lot of assumptions, but the nice thing at the end is that you can use it easily in a big 3D code. It's not clear that this works, okay? And there's been the topic of many papers. For example, can you use a manifold written for a diffusion flame in the case of a premixed flame? Can you do the other way? Can you use partially premixed flames, etc.? And does turbulence change that? Everyone says no, turbulence doesn't change that. It's the same manifold for laminar flames and turbulent flames. Otherwise, we would be dead. So I just want to show you two, again, you see where COE, again, is so important. Two examples where manifolds obviously must work. The first one is the diffusion flame using infinity fast chemistry, or something close to that. And the second one is the perfectly premixed flame, which we did yesterday. If you suppose that chemistry is very fast, we have shown yesterday that everything must lie on the equilibrium lines. So the equilibrium lines in an infinitely fast chemistry are a manifold. Okay? So if you can assume that the chemistry is infinitely fast, it will work. Of course, there's a lot of ifs here, okay? The flow must be adiabatic, chemistry must be infinitely fast, you must have only 2 inlets, not 3, that would be a problem. Then you can directly use a manifold which has only one variable. Everything is a function of z. Easy. So in that case, you would be stupid to solve for all the species, okay? It would be a waste of time. Just go straight for the tabulated. So that means that your code will look like this. Your 5 variables plus mixture fraction. And as soon as you get mixture fraction, you go here and you read Y fuel, Y O, and temperature. That's a case where obviously tabulations would work. Now the problem is that, by the way, it would depend on the flame that you compute. A flame like this one, which is lifted, where you see there is no combustion here and combustion starts here. This is reaction rate. This is the stoichiometric line. Obviously, this tabulation method would work here, but not at the bottom, because at the bottom we are on the mixing lines, we are not on the equilibrium lines, and then that won't work. So you have to be careful, but it's still a method which is used by a lot of people. Okay, people have picked up on this idea when you do tabulation, and it's like always, like a deep learning, you know, you say, oh, it doesn't work, so we can improve it. How can we improve it? Well, you can improve it by, for example, tabulating things not for a flame which is unstretched, but for a stretch flame, and you add stretch in your tabulation, one more variable. And that can be done. The other thing you can do once you have this type of tabulation is you can also add, if you do diffusion flame, scalar dissipation. You remember scalar dissipation? We talked about it yesterday. You can use stretch or scalar dissipation in your tabulation. But now your table becomes 3-dimensional. It may become a problem. Let me just jump also to this one. A lot of tabulations use stretch, but there are other things which are intuitive that you feel that you should use. One of them is the age of flamelets. What is the age? That's the Lagrangian age. When you are injected here, you have, for example, fuel and air. Here you start mixing. But you know, it takes a while before you ignite. It takes a certain time until you get old enough, and then suddenly you ignite. So the age should be somehow also in this model, and some models do that like CMC. You would like to go from the mixing line to something higher to go to the equilibrium line. And so this is something that you do more or less in the CMC models, which I did not describe this morning, which is an evolution of PDF models. But again, then things get complicated. The other case where tabulation will obviously work is perfectly premixed flames, which we did yesterday also. If you suppose that the flame is very lean, you know, you can replace, you say that this is equal to 1, and you can track only the fuel mass fraction. You know, we showed yesterday that then the fuel mass fraction depends on the temperature, so that you can use only temperature. And that's exactly the definition of tabulation. Actually, the formula for the reaction rate depends only on temperature, which is by definition what you want to do in a manifold. So you can also use a tabulated method if you do a perfectly premixed adiabatic flame. This is, for example, what was done here. So the simplest manifold that you will have in this case is written here. You will read the fuel mass fraction and you will deduce the temperature by saying that you have to be on this line, which is y plus theta equal unity. Okay? All the points must be on this line. So the gas entering is at the bottom here, and the gases leaving the chamber are on the top. Okay, I don't want to talk too much about the extensions because there are many extensions to that. The thing to remember is that when you do extensions, you need to increase the size of the table. And there are cases where the table actually takes more place than the CFD code. And so this is probably not the best thing to do. You want to stick to two variables. C and Z is probably the most reasonable thing to do. Okay, as I said, the nice thing is that somehow you have complex chemistry when you do that, but it's a frozen complex chemistry. It's the one which is tabulated. You cannot change it. So let me show you first the success of that. There are many groups doing that. Many of them actually are in this room, I guess. People have used that for many applications, but there are also limitations. I want to talk about the limitations in a second. I just want to say also that numerically for you it may be useful to use tabulation because in the tabulation you tabulate only physical results. In other words, when I give you C, you give me an omega dot which is physical. It was tabulated in a laminar flame. While in many codes, if you compute this thing in your code, if you have any errors, like 5 minutes ago I've shown you that fuel mass fractions or oxidizer mass fraction would become negative. If they become negative, the reaction rate will be crazy. That will not happen with tabulation. Tabulation forces the solution to remain within a certain interval, and that's of course quite favorable. Okay, so numerically there are advantages to tabulations. And of course, after you have finished your computation, you can post-process it for nothing, and you can get, NOx, CO, whatever, all the species. Since they have been tabulated, you can obtain them afterwards. Now, there are some limits. I want to talk about a few limits of that. One limit is, for example, if you want to do that in a piston engine, you have so many things to tabulate that you have 6, 7, or 8 parameters in the table. You have the heat losses, you have the pressure, you have the temperature, you have the dilution, you have blah, blah, blah. It gets crazy. And there are also one case, I just want to describe one case here, that's the non-adiabatic case. If the flow is not adiabatic, it gets difficult to tabulate things. I just want to show you one example that we did. That's a premixed flame stabilized on a cylinder. Okay, a very simple flame. So those are premixed gases arriving here on the cylinder. You can see the cylinder here. The flame is here. It's a premixed flame. And the thing about this thing is that the cylinder itself can be cooled by water or not. So depending on what's happening, here this is almost adiabatic, and here it is cooled. And you will see, of course, that if it is adiabatic on the right-hand side, then you can compute it with a manifold for adiabatic flames. But if you're on the left side, you can't. So that's a view of the flow. You can see the recirculation zone here. This is the heat release here, and here this is the temperature. And when you look at a flow like this one, we are changing temperature here of the flame holder. So we go from the adiabatic case to the cooled case. So now we are almost adiabatic. So you see the flame is very close to the flame holder, and then we cool it. And when we cool this thing, then the flame cannot go so close, and it's further away. Nice movies, huh? I like this one. So the important thing is that when we do the adiabatic case, we are definitely on the manifold. That means the fresh gases which come here are here, and the burnt gases which leave here are on this point. But when you go to the cooled flame holder, because you have heat losses here, these gases are those gases but cooled. So they are not on the manifold anymore, so you cannot use a tabulation anymore because you will arrive here. So as soon as the flow is non-adiabatic, you have to change that. Then people doing tabulation will tell you, okay, we can do a tabulation with heat losses. So that's one more dimension, and then things get difficult to evaluate. Okay, let me jump now to reduced schemes. If you don't like tabulations, there's another game you can play, is to use only global reactions which do what you want. And so typically here we have our 5 variables, and we'll use, a few global reactions, typically not more than 4 or 5, with maybe, you know, up to 10 species. And all these species now will be independent. So we'll be able to take into account heat losses. We'll be able to take into account a lot of things. The question is, how do we build these global schemes? Now, this is a game which has been here for a long time, especially here at Princeton. I mean, you look at the old papers of Westbrook and Dwyer. They've tried that for a long time. Many people have tried that. They've tried to build up a scheme which would have only, you know, 2, 3, 4 reactions and which would capture most of what's important. It is an interesting exercise because you can play with the pre-exponential constant of each reaction, with the activation energy, with the temperature exponents, with everything. I think also Moshe mentioned that this morning. Those are the schemes where you end up with a chemical reaction which can have negative exponents. You can have something like a pre-exponential constant, YCH4 to the power minus 0.3, okay? Which is, when YCH4 goes to 0, a problem. But anyway, this is a fitting exercise where you try to fit things so that you can, with these parameters, mix here, you can fit the full data. So how do you do that? Well, usually you say, I want a scheme which can capture the laminar flame speed, which can give us the right flame temperature, and the right CO2 and CO, for example. And then you start fitting this thing. You can do that with genetic algorithm. You could do that with AI, actually. You can also just ask the PhD to do it in some way. His problem. Why does it work, actually? As you will see, it works really well. And the reason it works quite well is because when you do that, you don't try to fit a scheme to do all composition, pressure, and temperature. You just try to tell him, OK, I'm doing a chamber at 10 bar, 300K, please build me a scheme which does just that. And the way you do that is that you need a full scheme, okay? You need Cantera, obviously, with a full scheme for your fuel. And then you have your reduced scheme that you can run on your laptop, and you tune it until you can compute the target flames and match them by, you know, fitting things, as I said, automatically or by hand. Then once it's done, you can use your reduced scheme in a 3D code like we did for tabulation. Again, it works really well because you are not very ambitious. You don't try to find a scheme for CH4 which does all conditions. You just try to find a scheme which can do the case that you want. So let me give example. Here we're going to do methane. And as you see, methane, here we do with only one reaction. That's not much, okay? It's difficult to do less. So you take one reaction, you write it like this, and then after you tune the result, here's what you obtain. Let me go back. That's the adiabatic flame temperature as a function of equivalence ratio. So you see that the blue line here is the reduced scheme. And you see that, of course, compared to full chemistry, you are bad here. But if you're computing a case at 0.8, you're pretty good. Why would you, introduce 20 more species to do something which has no interest for you? If you're doing a premixed flame here, you see that all this range is really well captured with that. It will be a waste of time. It will be also a waste of points. All the time that you're losing by doing a full scheme, you could use it to do better resolution. And then when you look, at the flame speed, you see also that the flame speed is extremely good here. Of course, it's not good for which cases, okay, but if you are doing a lean flame, why do more? Now, I remind you also that anyway, the precision of the full scheme is not that big, okay? Those are all these points here are distributed. So you see that the reduced scheme here, which is extremely cheap, is very good for the flame speed until, maybe 1 or something. At least it is clearly within the range of the margin of errors of the full scheme. So we should not worry too much about it. It's probably sufficient. Now, you can do better. The first thing you do when you do one-step chemistry is that you go usually to two-step. That means you add the CO-CO2 equilibrium. Why you do that? Well, because the fact that temperature is too high here comes from the fact that you don't have CO. As soon as you add CO, this relation here in your scheme, the temperature goes from here to there, and you see that you are right on the exact solution. So just by adding CO, you can be very good for the flame temperature, and you see that you are pretty good also for SL up to, equivalence ratio of 1 or something, and that doesn't really cost more. You're computing CO also in the burnt gases. Here, O2, CH4, whatever, you see that the agreement is really good. And again, remember that this is 20 times less expensive than running GRIMEC, for example. So again, if you want to do a full 3D computation, please don't use GRIMEC. If it is fully premixed, use a two-step scheme. That's quite sufficient. Now you can actually do better than that. You can say instead of having a fixed reaction rate here, I can start playing with the pre-exponential constant, the exponents here, and the activation temperature to fit other cases. And this game also has been going on for a long time. I think there are a pretty good paper by the Spanish group here. And we did it also, and we did it by just teaching one thing, only one thing, that's the pre-exponential constant. We allow ourselves to change the pre-exponential constant as a function of the equivalence ratio. And when you do that, you have one of the most famous schemes here in the field, which is the BFER scheme for methane. A lot of people use it because, as you can see here, it is very good over a wide range of pressure and of temperatures just because we have tabulated the pre-exponential constant. And the results for flame speed are just much more than what you need. So a lot of people doing methane computation actually use this scheme because it's the best compromise in terms of precision versus the cost. Of course, you can try to use GRIMEC if you want, but I'll be waiting for you, until you get the results because the cost is going to be 20 times more. Now, I want to finish here by talking about analytical schemes. These schemes have been developed in the last 10 years, and they are interesting because they want to mimic the global schemes, but they want to do it in a smart way, let's say from mathematicians. And let me tell you the principle of that. When the scheme I've shown you just before is built in a way so that we don't use at all the information we have from full schemes. We just try to mimic them. But you can do better than that. You can actually take the full schemes and start from the full scheme and go to a reduced scheme by using some mathematical methods developed by theoreticians and by people like Allison to do that. And it works. It didn't work in the old days, but today it works quite well. So instead of having only 2 steps, maybe we will allow us to go maybe to 10 or 20, and maybe instead of 6 species, we go to 25, but all of this will come from the full chemistry, not from some ad hoc method to try to tune things. And for you, when you look at your CFD code, it doesn't make a difference, okay? It's 200 lines in the CFD code, so it will be still cheap, reasonably cheap, let's say, compared to a full scheme. These methods are not new. If you read, actually, again, in all these papers, somehow you find Ed law somewhere. So that's one of the papers of Ed, when they did it, 15 years ago with Tianfeng Lu, and they proposed already this method. So let me just describe roughly the principle of the method. You start from a mechanism, which is a crazy mechanism, hundreds of species, thousands of reactions. You give it to this code, and the code looks at species and reactions and starts eliminating those which are not important. Sounds easy to say, okay? Mathematically, it's difficult. And you end up with what you call a skeletal mechanism. The skeletal mechanism is supposed to have the main important information and not the details of the scheme. But now this guy usually still is too big to go into a CFD code. So you do one more thing. You go to a setup where you start eliminating things here. For example, reactions which are quasi-steady state. You eliminate them, you replace them. Everything is done automatically. And at the end, you come out with, typically 20 species. So I'm going to show you what that gives for methane, because again, methane is really the first gas you would want to do. You start from GRI. So this is a monster, okay? You cannot do that in a CFD code in 3D. It's crazy. So you use this method, you come up with an arc scheme here, and you can directly plug it into your code. By the way, if you're a PhD student, these things are available. You just contact people, they can send you these things, they are open source. So there's a long list of mathematical procedure to go to there. Let me just show you the result. Okay, so here the target was to build a scheme which would work between 0.6 and 1.4 at 1 bar and 300 K, and to be able to predict everything, flame speed, heat release, CO, and NO. And so you run this code, and you end up with this scheme here. This scheme, then you can test it. When you test it, you test it on a few flames. In this scheme, you're going to transport 22 species. It's not small, but it's still reasonable. You will have what we call quasi-steady-state species, which are not explicitly tracked, but you can always obtain from the previous one because there are algebraic expressions from the previous one. So if you look at the flame speed here, at the CO emissions and at the NO emissions, you see that for this flame, you are right on it, okay? It's perfect. So you see that this procedure, which you don't have to worry about, someone will do it for you, works extremely well. And today, for example, at Surfax, students take this tool and 1 week later they get their scheme, okay? It's not a problem. So that's working. The nice thing is that it works really well at 300K 1 bar, but then you go to 700K and 3 bars and 6 bars, and it works as well, okay? And that's what's new. Why does it work? Because it keeps all the intrinsic qualities of the initial full scheme, okay? It still knows that it is a full scheme initially, so that you can do another flame here, another premixed flame, and it's still working extremely well. Now, you can even go to diffusion flames. That's when it gets very interesting. This scheme was written for a premixed flame, but now you use it for a diffusion flame, and you see that it's perfect again for a diffusion flame. And that's really something we need not have with global reaction schemes. BFER, for example, I've shown you if you want to do it in diffusion, it's not going to work. So you see here there's a price to pay for that, but it is reasonable enough. And there are many groups today which do all their LES with this type of scheme. So I really believe that this is going to be the standard tool for the future. Okay, I think I'm going to stop here for the moment, so we can take a few questions if you want before we go for a break. Yes?
What is the price?
The price of a computation is proportional to the number of species. So you start from, we had 5 plus 6 when we do a reduced scheme, that's about 11. Here we have 5 plus 20, that's 25. So the price is about 25 divided by 11, it's 2.5. You don't lose anything, it's much better in terms of accuracy if you use the ARC scheme, but you need to pay 2 to 5 times more. But the accuracy is, in terms of chemistry, the accuracy is better, of course. And of course, you're losing human time because you need to code all that, okay? You still need to make your code compatible with this thing. Yes?
You mentioned the desire for breakup and quenching grids for LES purposes, but that struggles with more geometry. I'm curious about your thoughts on better boundary methods, which I think are on the second order right now. But,
Okay, I think the case is still open. The community is split in two today. You get the LBM guys and Converge guys doing Cartesian grid and something at the walls, which they claim to be good, which we don't believe it's good. And you get the unstructured people like us, which do body fitting coordinates and meshes. And I think the case is open today. I think there are cases where, when you go to piston engines, for example, the capacity of meshing easily with Converge overwhelms the other arguments. We've been doing piston engine computation with unstructured grids for a long time, and they were just too long in terms of human time to generate the mesh. But there are other cases where it's not the case. For gas turbines, Converge is probably not as good as what we do. So I think the case is open, and clearly the weak point of Converge or of LBM method is what do you do exactly at the walls. That when you get this cut cell method, it's still difficult to see how this can be as precise as a body-fitted method. You go to talk to people we work a lot with people at Airbus, they wouldn't touch this thing on a wing. You know, so, whoa. You cannot do something precise at a wing with that. But I think the competition is clearly open there. You have to, if you do a regular mesh, you know, IJK mesh, you cannot live if you don't have AMR and automatic reduction method to focus, because some details actually will not even appear in your mesh. If you're trying to mesh a swirler, for example, you need to do mesh refinement. Absolutely, yeah. Not only cut cell plus, well, Converge has that, okay? You can zoom in and, yeah. Yeah. It's the same. The point of the upwind scheme is that, like artificial viscosity, they add viscosity everywhere, and you don't want that. So if you can do an upwind scheme, some schemes do that, they upwind only in certain regions of the flow, that would work. What you don't want is to have an upwind scheme everywhere, because that will just be too dissipative. No question left before coffee? Okay, we go back in 10 minutes. Right now. So before, I want to bring in combustion stabilities now. But before doing that, I want to say a few words about HPC. Because if you're doing a thesis on CFD, you will not escape from that. The main issue with these turbulence simulations, as you have seen, is that as the Reynolds number goes up, obviously the number of points goes up. And I see a lot of people, asking me, what size of a machine would you need to solve your problem? And I always say infinite, because the Reynolds number goes to infinity and the number of points goes to infinity. So there's no limit to the power that you guys can use if you want to do a turbulence case. So you have to stop at some point. But the point is that we should use as big machine as we can. And that's a big issue. These machines are huge already. We're talking about the numbers you have to keep in mind is $100 million for the machine and $20 million for the electricity per year. Okay? People complain about the cost of electricity, but this is really costly. And of course, these machines change fast, and we are not their target. Okay? Well, some of you are. Those who play on their computer, you are the target. Video games are what's driving the market, not supercomputing, which means that every 2 years, the machines on which we compute are changing. This is why we're going to GPUs. GPUs were not big a few years ago. They are going to be big soon because GPUs are used to play video games, not to do CFD. The problem is that means that we need to change our codes every 2 years. And the code I've been showing you for the last 2 days is 1 million lines. Okay, so if you have to change a 1 million line code, it's a pain. These machines today, this is the top 500. A few months ago, the first machine here has 7.6 million processors. Okay, which means you might decide you want to do a PhD on your laptop with one processor. But of course, if you are competing against a guy who can use 1 million cores, you're going to do a 100 by 100 by 100 case while he's going to do a 10,000 by 10,000 by 10,000. And guess who is going to be published? No, it's going to be tough. So to compete, when you do CFD today, you need to have a high-performance computer. And you know that the equations that we solve, we've talked about that many times. We're talking about, let's say, 10 to maybe 100 species. We need to add all these models. We need to have a mesh which contains billions of points. So typically, we're talking about something like 100 million cells. That's typical today of an LES for a PhD with 20 species. And we run that, let's say, 1 million iterations. So we generate 10 to the power 16 unknowns. So this thing is getting out of control, okay? So learning about HPC is mandatory for you, okay, if you want to do serious DNS or LES. Remember also, this is all parallel. So the message passing is a problem. And so you need to learn these things, even if you don't want to, or you need to find a friend to do it for you. Because having all these players play together, because that's what we're talking about, is tough. So the way you do that, most codes today do the same thing. They do domain decomposition. That means each part of the space here is cut into a small piece and given to one processor, and the next one to another processor, etc. There are other ways to do parallelization, but this is one way to do it, and that most codes to do that. Now, you have to know that every time you parallelize a code on 10 times more processors, it's a different game. It gets actually much more complicated. So it's not the same, if you have a code running on 100 processors, don't believe it's going to run on 1,000. To go to 1,000, you probably have to rewrite it. And then if you want to go to 10,000, same thing again. So it is not a detail. I just want to take one example so that you understand the types of problems that you're facing here. If you're doing a code which is explicit in time, before you even start doing any simulation, you have to decide on the time step. And you know the time step is usually determined by the fact that the sound speed multiplied by the time step divided by the space mesh must be less than 1. Depends on the code. If you do explicit code, compressible code, this will be 0.9 or whatever. And so you need to know the minimum of nu delta x divided by AI over all your mesh. But the problem is that when you're sitting on one processor, you don't know the other processors. So you need to gather all the information from the whole mesh and then to do the min, and then you need to resend the information. Again, on one processor, this thing, you would just do a loop, do I equal 1 to n. But on a parallel machine, you don't have the data on the same processor. So that looks like a simple process to do. Usually, in certain codes, you have what we call a master, and the master will just, ask to the slaves here. Each slave has a little bit of the domain. It will ask what is the time step. So the first thing to do is that you get all this data from the other processors, you gather them, and then once you have determined the time step, you have to send it back to each processor. Looks like a very simple thing to do. There are methodologies to do that. MPI typically allows you to receive a message and to send the message. So on the paper, it's easy. So the problem is when we did that in our code on 10 processors, 100 processors, 1,000 cores, works really well, and then suddenly at 10,000, we found out that this process was actually which was the biggest process of the whole thing. The Navier-Stokes resolution was faster. Why? Because we had this problem of communication. Because the problem is that, that's the main problem when you have 100,000 processors. If one of them has to do something in common for all the others are waiting and saying, okay, when you want, I'm ready. Send me the time step. And then the poor master has to process everything. Everyone is waiting for him. And so there's a simple fix to that. And the fix is the following. Initially, what the master was doing, it was sending the time step to every slave. But then you can do something better. You can say, okay, I'm the master, I'm sending him the time step. Now, instead of sleeping here, you can wake up and send the time step to the guy behind you. So, I will be sending the time step to the second slave. In the meantime, you will be sending it to this guy. Then this guy can send him to the other guy here. And you see that then the time step will propagate much faster through the grid, okay? So it's quite easy. You just ask the guy who knows the code to manipulate MPI in a different way, and you speed up the code. This 20% become again 0.1%, and you say, wow, it's great. The problem is that the way you do this operation is not the same on an Intel machine or on a GPU machine. So you say, okay, no problem, we'll do 2 versions. And then that's the end, okay? As soon as you do 2 versions, pretty soon you have 20 versions. And then when the PhD student arrives, he has to find the version of Albert multiplied by the version of Jan, composed with the version, and then nothing works anymore. So the multiplication of versions is the kiss of death for code, okay? There are too many versions, you are dead. So you see that a simple problem like this one, when you go to reality, becomes your problem if you're doing a PhD. You don't do physics anymore. You are just fighting with stupid computer problems. But you have to face them. But again, the main issue here is that the Navier-Stokes equations are difficult to parallelize. So you shouldn't try to do that on your own. You have really to find a way to collaborate in a big team so that you can have a good code to do that. They are basic. I know that some of you are using OpenFOAM. You need to be in a community to do that. The old days where you could do that on your own, unfortunately, are over. I just want to finish here by just mentioning the kind of performance that you should expect, okay? This is the performance of AVBP, the code we use at Surfax. Typically, 130,000 processors here for a speed up of 100,000. Of course, if you are running 100,000 times faster than your neighbor, it's going to help you. Huh? I just want also to say a few things here about what we see as a community here. It is true that we talk here about turbulent combustion, we talk about combustion theory, and a lot of people keep saying, well, we don't need all that if we do DNS everywhere. If we do DNS, we don't need a model. We don't even need theory, we just run the code, okay? Well, probably it is true because you see, for example, high-order turbulence models, like Reynolds stress models, I'm sure that many of you have never even heard about it. It was a big, big thing 30 years ago, and then it's forgotten today. Analytical methods, fortunately, we have Moshe here, but you know that people like Moshe are becoming extremely rare. When I'm looking for a review for combustion and flame who knows theory, I don't have a long list, and that's bad. So the question is really, are we going to be able to do DNS everywhere? I don't believe so. I've shown you the numbers. We don't have measures with 10 to the power 24 points. It will not happen, not ever probably. So, and I want to show you also that there are cases where you will still need to think about things. The first one is pressure. The other one is size. I will talk about size tomorrow, but let's talk about pressure. You see, I've shown you that the Reynolds number was the key question of our problem. When you go in high pressure systems, everything becomes much more difficult. Why? Well, if you go again to theory, you know that the kinematic viscosity decreases like 1/p. So when you go to a pressure of 20 bar, all the Reynolds numbers are going to be increased by 20. And 20, as you've seen, is a big number. Everything will become smaller. The small eddies will be smaller. The flame thicknesses will become smaller. And so it really means that it's quite unlikely that we'll be able to do DNS there. I just want to show you that in a diagram here where we plot the Reynolds number as a function of pressure and size. And you see here, if this is the size of the system you want to compute, and if this is the pressure, when you do a PhD, usually you're looking at a small chamber at 1 bar. Okay, so you are here. So you may think that you are good, you know, that because you get the results of the experiment. But unfortunately, when you go to industry, the real gas turbines are 20, 40 bars. And we'll talk also tomorrow when we talk about hydrogen of the larger domains. For example, when you do explosions, you have to do a 50 meters domain. So there, the problem will be that we may be good here and extremely bad here. And so we will not be able to do DNS everywhere. We might be able to do DNS here if it's not too big, but not at the top level. So we will keep having to work on models and on turbulent combustion models, even if DNS might replace everything, but I don't believe that. Okay, we finished with an introduction to a fun topic, which we touched already since we started talking about acoustics, and that's combustion instabilities. Okay, this will be noise, so I need to move that a bit. So that's an example of combustion instabilities in an analog system. You can hear the noise, and we'll come back to that in a minute. We'll talk about acoustics today. Acoustics can be not only noisy, but also jumping because of combustion instabilities. So we need to talk about that. We need to talk about that because many of you actually, even in LES or in experiments, will hit on combustion instabilities, and it's good that you know what to expect. So I just want to remind you that instabilities are found everywhere in mechanics. Okay? The way you design systems in mechanics is that you show an equilibrium state, and then the question is it stable or not? You know that this is stable and this is not so stable, and sometimes you find out a little bit too late that it was unstable. Like the famous Tacoma Bridge, probably you heard about it. This is without combustion, but if you add combustion, because of the huge power which is there, these things can become extremely unpleasant, extremely fast. So in combustion, you have multiple instabilities. You have to be careful about the word instabilities. For example, when you inject liquid fuel into a chamber, that's the instabilities of the interface which create the droplets. That's one type of instabilities. If you look at kinetics, Moshe will show you thermodiffusive instabilities tomorrow, I guess, when you see cells forming, and that's one type of instability. Of course, you have also instabilities when the combustor gets coupled. That's the case for rockets, for example, with the tank. And then you start having oscillations. That's also an instability. And we have classified them in the combustion world as a function of size, basically. Intrinsic instabilities are instabilities appearing on the flame front, typically. Chamber instabilities are instabilities linked to the whole combustion chamber. And system instabilities are instabilities which involve the whole aircraft or the whole system, okay? So the size goes up. Those here, the intrinsic instabilities are not really of a problem. They are small. Those we don't have to study in the combustion community. It's not our problem. Someone else has to handle them. But those here are what I want to talk about. Now, just a word about intrinsic instabilities. You've seen them already. Normally, a flame is smooth. But if you go to low Lewis number, you start developing cells. That's a type of instabilities, but it doesn't hurt anyone, okay? So I don't want to talk about that one. You've seen these pictures already. There was one by Moshe this morning. It's a classic in the combustion community. Let's go to, that's also actually a simulation. You can have these things also in simulation when you form these instabilities, and we'll talk about them when we talk about hydrogen. Let me just go to the other side now. The system instabilities, the most famous one is what we call the pogo effect, which is more or less controlled today, where there was a resonance between the tank, the structure, and the engine, which basically blew up the whole satellite. But again, this is not the problem I want to discuss today. I want to talk about chamber instabilities and about thermoacoustics. So here, it's very simple. You see the effects of thermoacoustics here, okay? That's a chamber submitted to thermoacoustic instabilities. Obviously, this is an important problem. If you have it, it's the end of the story. So this is the main topic today. We call these instabilities acoustic combustion instabilities or thermoacoustics, and this is a main topic. So to understand combustion instabilities, you need to understand that flames and noise, and flames and acoustics, if you want, are connected. They live in the same world. And normally, they don't interact too much. For example, you have a flame here, which makes noise. Well, the noise goes away, okay? And the only interaction between the two is that you generate noise, and then the noise goes away. Fine. It's a problem in itself, okay? When you do acoustics, you have to care about it, but it's not the main problem. But now there are cases where you have confined flames. Now, the noise produced by the flame cannot go away. It will hit the walls, and as I've shown you in the movie, come back to the chamber. If it comes back at random times, it's not a problem. But if it starts coming back at the wrong time, if I can say so, it can change the flame, which will make a new acoustic wave, which will bounce on the walls, come back, and then the whole thing can become crazy. And that's when we have a combustion instability. Okay, so here I need to mention a few things about fluid mechanics and instability theories. There are two types of instabilities in fluid mechanics in general, the convective and the absolute. So what's the difference? The convective instabilities, if you plot them as a function of time and x, if you make a perturbation here, like you go in a river, you throw something in the river, you will see waves, but these waves will be convected away. So if you come back here after a certain time, you will see that the wave that you introduced has been pushed away in the river. It's going away. So if you wait long enough, everything will be gone. So if you throw something in the river, after 1 hour, nothing will be left. Fine. The resonator is not working that way. The resonator is something where you throw something in the river, and then the whole thing starts oscillating, okay? The classical example, you have a rocket engine, you push it, and then this thing starts vibrating and exploding. That's bad. So that's what we want to avoid, the resonators. There's a big theory on that by Mankiewicz and Huer from USC, and I don't need to go into that. The only thing I want to mention is that somehow you feel that to have a resonator, you must have some kind of feedback mechanism. You throw something in the river, and somehow the information comes back to feed again another perturbation. So you need some kind of negative velocity to have a resonator. So the system in general looks like this. You will have a flow somewhere, and if you have a convective instability, you put something at the inlet, it goes to the outlet, but if you stop perturbing the inlet, it will stop at the outlet. while if you go to a resonator, the flow now sending back some information to the inlet, and the whole thing starts turning, and if you have done some control theory, you know that this thing is not a good idea. Okay, in combustion, the way it works is actually rather simple. We know that we are creating a vortex, that this vortex will burn. When the vortex will burn, it will create a pressure wave. The pressure wave will actually come back because of acoustics, because acoustic waves propagate in all directions, including upstream. The acoustic waves are going back here, reflecting and coming back again, and then they create another vortex, and then this thing starts again. In this simulation, we don't introduce the vortices. This thing becomes unstable on its own, and it starts, a combustion instability. So, in combustion chambers, since we have acoustics, but since we also have recirculation zones when we are swirling, there are many things which can actually lead to resonators, the sound and the recirculation. So in a swirl flow, many things can lead to instabilities, and many things do. So this is why we have so many people looking at this problem. These instabilities are, of course, dangerous. I've shown you many examples where when these things start building up, they can generate vibrations, they can quench the flame, they can make the system explode. I mean, there are lots of examples. And interestingly, we've known them for a long, long time. The first papers on combustion instabilities is Rayleigh, 1878. And he already indicated everything which we're going to discuss today. So this guy was smart. So why do we have instabilities? First thing to remember is that flames make noise. Okay, I didn't show that yet, but you can prove. It's quite easy, actually. You read these papers here, it's 2 lines. You can prove that the pressure anywhere near a flame is proportional to the variation of heat release. So if you take a steady flame, there is no variation of heat release, there is no noise. Okay? If you take a flame which is moving, there will be a dq dt, so there will be a pressure. And they are related by this very simple formula. Okay, so if you measure the pressure, you could actually guess how much of the heat release here is changing. So you can visualize that here. This is a flame where we create vortices, and you see here we have plotted divergence of hue. That's the dilatation, that's the noise. And you see that every time here there is a big change of flame surface, it's a big change of Q, bling, boop, it makes noise. Okay? But you know that the flame makes noise. Okay? That's just a way to visualize it. You can actually even hear it. This is I had a student doing a CFD PhD, so he wanted to do experiments, so he did that at home. So that's just an example of a tube. Here first without flame, and actually the noise is so low that you don't even hear it, so you just have jet noise here. Then you ignite the flame, and you see there is an additional noise compared to the case without flame, and you can actually do an FFT. So here you put the frequency, and then you see that without flame you have this noise, and then when you go to full throttle here with combustion, you have what we call a broadband rumble, where this thing makes noise, okay? This is not unstable yet. I will tell you later why. This is still a quiet flame compared to what we will have later. Now, as I said, if the box is closed now, like it is the case for all engines, the box is closed, the acoustic waves will bounce on the walls and come back to the chamber by many ways. There are so many passes to do that, it's difficult to list them. But they can come back to the flame zone. And then we hit the second problem, which is flames are sensitive to noise. I've told you that they are creating noise, but they are also sensitive to noise, because noise is associated to a velocity change. Okay? And velocity of a flame is not much. It's easy. You know how to do that. You take a flame, you blow on it, poof, it moves away. Okay? So flames are quite sensitive to noise. So let me show you a few fun examples of that. That's a classic movie in our community done at the M2C in Central. So they have a loudspeaker here, and then sending waves on the flame. Okay? And you see how the flame reacts for this. It's a Bunsen flame, the same one that was shown this morning by Moshe. And you see the noise, that's a natural noise that you hear at the same level. It's not that big, but that's sufficient to make this flame crazy. Now, this property can be illustrated also if you have a Colombian PhD student like me. We had this experiment in Toulouse. So this is a case where you have 7 flames now, and he had a loudspeaker at the bottom of it. So he used to send harmonic waves, but from time to time he would do something else, like this one here.
This time for Africa. Samina, mina, waka, waka, samina, mina, sakalewa.
Looks well, huh? So those are examples where you see now that flames make noise and flames are sensitive to noise. So you can have a loop. Now, you can produce acoustic waves, and then these acoustic waves can perturb the flame and then create an amplification loop. You can actually even use that to make music. You can create an instrument working with a flame. If you tune here small tubes with flames at the bottom, you can use it to make music. Most labs doing combustion stabilities have one in the lobby for the students.
Sa propre fréquence, mais l'énergie de la vibration, l'entretien du
You have to
son
speak
est
French or you
apporté
can
par
read
la
the
flamme.
subtitles.
Ce système est typique donc des instabilités de combustion que l'on peut rencontrer dans des foyers industriels.
So you see that all these things are fun if you do them in the lab for a small flame and nothing really bad happens. But then, that's not so much fun. That's a swirled combustion chamber in Germany, and believe me, the noise is not what you expect. Normally, it should be quieter than that. And when you start having this kind of behavior, right away, you see also that the walls are getting quite hot. And usually you break the chamber after a few minutes. And in a big engine, in a fighter engine, the lifetime of a fighter engine submitted to combustion stabilities is half a second. It's a problem actually because the pilot doesn't even have time to get ejected. So these things are fun from the fundamental point of view and critical for industry. So I think I have another fun example because these things take all kinds of shapes, like this one. Different frequency here, you see the flames jumping. If you want to do an experiment here, you are stuck with instabilities, okay? Another one. I have a long list. So you see, these instabilities are not exceptional events. You hit them quite often. Not all companies have the problem, but many of them have the problem. So just a first element here of giving dimensions. You see that if these things are associated to acoustics, they must scale with the acoustic timescales. So what is the acoustic timescale? So you see typically here, if you look at the time it takes for an acoustic wave to propagate from the bottom to the top and come back, it's about 2 times L over C. And if you look at the sound speed with the number we have, it's about 700 hertz. And that's what we will see in most chambers. Most chambers are of the order of 50 centimeters. And so the combustion stabilities will be between 100 and 2000 hertz, something like this. So when you will hear a very sharp noise in a chamber at this type of frequency, you might be able to guess that you probably have a problem of combustion stabilities. Now, I don't want to describe swirl again because we did that already. Swirl participate to this problem, okay? Because swirl is a nice thing to stabilize flame. I already showed you this type of picture. You know that when you add swirl in a chamber, it creates a huge recirculation zone, and that this zone, where at very high swirl, is helpful to stabilize the flame. But unfortunately, swirl also leads to instabilities. A swirl flow has this capacity of developing instabilities, which are a problem. I just want to show you an example here of swirl flame so that you can see how we do that in practice. This is the way you create swirl. You have these veins here so that the air is turning. Oh, it's gone. This is the way you introduce the swirl in your system. Normally, everything here should just rotate around the axis. And so that would create a stable recirculation zone. But unfortunately, like always, nature doesn't always do what you want. I just want to show you also this one. That's an Alstom gas turbine, where you can see that the flow is swirled here because the flow is entering like this and here, so it's turning, and it's creating the zone here where the flame is stabilized. And so everything should be good if swirl would be a stable flow. Unfortunately, swirl develops instabilities also that you can see here. You know, it starts, instead of being perfectly aligned with the axis, it starts, you know, moving around. You've seen actually swirl flows before because this is what you have in the contrails of aircraft. And the problem about this rotation is that everything that turns can become unstable. And this was actually a theorem that probably the French know about it, you don't. There's a famous French mathematician, not from my family, which his name is on the Eiffel Tower, you know, so I can say I have my name on the Eiffel Tower, it's not me. He was the one talking about precession. Precession is the fact that if something is turning normally, the axis of rotation pretty soon starts turning. And that's okay, but except for swirling flows, it has bad consequences. Because in a combustor, what happens is that the axis of rotation of swirl starts also to turn, and that generates problems. In the air, the first instability you see, you know, you will watch tonight, you know, swirl, the contrails. The contrails usually don't stay like this, they connect to each other, and they do all kinds of funny things because these things are quite sensitive to instabilities. And in a turbulent flow for a combustor, what happens is that the axis of rotation also starts turning, giving us this helix formation, which is not good for combustion instability. So let me just show you an image here of an LES. The white surface is an iso surface of temperature, so this is where you have the hot gases. And the red one is an iso surface of pressure, which shows you the center of the vortex. And you will see that these two things live together in a complicated way. You see here the axis of rotation turns, and the flame is organized around it, so that's an additional instability. And in swirled chambers, we have both acoustic waves and we have these animals here in the center of the chamber. And again, in the community at the moment, you see hundreds of papers trying to elucidate the links between the two. Okay, so as I said, this topic is not a classical one. If you need to work on it, I guess probably the good places to start is this classic book here by Crichton and et al. There's a lot also in my book, and Williams has a pretty good description of that. I just want to say that these instabilities usually have you stop your experiment in many cases. This is a map of operation in many burners. You know, you plot here the occurrence ratio, here you put the airflow rate or the power, and usually, you know, there are many cases where you don't have combustion, and in many of these cases, you don't have combustion because if you go there, everything starts vibrating so much that the PhD student stops everything. Soon enough, sometimes too late. So the fact that you cannot go there is a problem. There are many systems like ramjets, for example, where you have to, in the operating domain, you have to try to avoid this, well, you don't try, you have to avoid these zones because you know that if you enter this zone, this thing is going to explode. So it is a big problem of operability in many engines. So to try to tell you now, after you know the phenomenology, to try to show you how to use the tools that you have today, I want to illustrate that by talking about the two methods that we use to do that. The one method to understand instabilities would be to linearize the equations and to look for the eigenmode. Okay, this is exactly what Moshe has been doing this morning, except we're talking about a 3D reacting flow, so it's not that easy to do, and I'm not going to do it today. The other way to do that, and then you will recognize it in a few minutes, is to define an energy of the system and to see if this energy is growing or if it's not growing. And if it's growing, we can find a criterion for instability. And that's what I want to do today before we finish. So before I do it for flames, I'm going to do it in a simple case, okay? So that you don't get lost. Let's look at the pendulum. Well, it's not a pendulum, it's an oscillator. You all know that. This pendulum, you know the equation, okay? M multiplied by the acceleration plus kx equals 0. And you know how to solve that. You know it's going to be an exponential solution. You plug it here, and you find the pulsation. So here, this is the hard way, I would say. You have the equation, you solve it. and you find that this is something which can oscillate, and you all know that a pendulum can oscillate, and you can find the pulsation frequency. Now, if you talk about the energy method, it will not work like this way. The energy method will take this equation and instead of solving it, would multiply it by x dot and integrate it to find that 1/2 mv square plus 1/2 k square equal E. And we would say that E is the total energy of the system. And at that point, it's not really useful to do that because you didn't solve the equation. You just can say that in this system, the sum of the kinetic energy and of the potential energy is a constant. And for this case, of course, there is no advantage to do that. But suppose now that we don't do this oscillator like this, but we do the oscillator with forcing, F. I don't tell you what F is. I'm pushing the pendulum. Okay? I don't have to tell you for the moment how I do that. You cannot solve this equation if I don't give you F. Okay? But with the second method, you can use it because you can multiply this equation by velocity and integrate it. And you see that you find something fun here. You find that the energy of the system now is E plus the integral of Fv dt. And that now this energy will grow or decay depending on the sign of this thing. And you see that I can build an energy criterion now just by saying that if integral of Fv dt is positive, then this thing will oscillate more and more. So this is what we call an instability criterion, and in a few minutes I will do the same thing for a flame. What does this criterion say? It says that if you push when the velocity is positive, you will increase the system. So if you have a little sister, little brother on a swing, you know that, when you have to push when it's going away. If you push at the other time, you will slow it down. So that's a simple criterion of instability. I'm going to derive now the same thing for a flame. Okay, if you push a swing, you know that, okay? You have to push when velocity is positive. Now, same thing for a flame, except it's a little bit more complicated, but you should find your way. Okay, this thing we've done already, so you know about acoustic waves. I'm going to jump right away to the derivation of the flame, and it's this one. A few minutes ago, we derived equations for acoustics in an isentropic flow. If the flow is not isentropic, if you have a flame, it's, of course, entropy is not conserved, then you have to do the same thing I did before, but now you have to add the temperature equation. Now you should know it by heart, okay? This is the equation of Moshe also. You take these equations and you can linearize them. Exactly like I did a few minutes ago. You say density is constant plus a perturbation, pressure is constant plus a perturbation, temperature, velocity, the mean velocity is 0. You plug that into the equation, you find the one we had before, continuity and momentum, except that now you also have the temperature equation. Temperature equation has been linearized here, and we can combine all of them to obtain a new equation for the energy. And you see that you recover the equation that we had an hour ago. So this is the acoustic energy. This is the flux of energy. And look here, there is a new term, P prime multiplied by omega prime T, which is the unsteady heat release, normalized by some constant. Now this equation is the acoustic energy in a combustion chamber. And it tells you that the acoustic energy in your combustion chamber will do nothing funny if this term is not doing anything funny. In other words, if this term is not positive, you're good. If this term is positive, you're in trouble, potentially. And that's something we call the criterion of instability, exactly like the pendulum, except now it's for combustion. And if you integrate it over the whole chamber, you find this equation. The total energy in a combustor plus the flux of energy at the walls, at the inlet, at the outlet, this is all integrated here, equal the integral of omega prime P prime dV. And you see that now you go to this famous, it's probably the only thing you will remember from the combustion stability theory, it's that if omega prime and P prime are in phase, or at least let's say if their integral over time and space is positive, then you can have combustion instability. And that's the main criterion for instability. If you release heat when the pressure is positive, exactly like when you push the pendulum, when the velocity is positive, you're doing something stupid, okay? And that's what Rayleigh said in his own words. I think I have the sentence here. No, I didn't keep. Yeah, that's the sentence of Rayleigh. You have to read English of that time, you know. But if heat is given to the air at the moment of greatest condensation, that means when pressure is high, or taken from it, it works the other way too. If pressure is low and you remove heat, you get the same result. Then you get more vibration, okay? And that's in this paper, is 1878. So it really means that exactly like you have a stability criterion for a pendulum, you have a stability criterion for a flame. And if you're not careful, the flame will start oscillating. And as you have seen, the consequences can be extremely bad. Now, this criterion of instability is only true at the beginning. When the flame starts oscillating, then the question of what happens later is another question. A lot of things may happen. The first thing which can happen is that you go to what we call a limit cycle. That means this thing oscillates, it makes noise, and nothing else happens, which is, you know, okay. The theories of Rayleigh does not apply here. It applies only here at the initial moments. When you go to the limit cycle, it's too late. And here, if you want to study limit cycles, it's a much more complicated problem. But this limit cycle is not necessarily what's happening. In many cases, the combustor will not go to that. In many cases, the combustor will just explode before that. Okay? That's, of course, end of the story. But there are other solutions. In an industrial gas turbines, you get accelerometers everywhere. And if they detect that the vibration is high, they just cut the gas. Okay? Don't want to break it. And they call Siemens, and Siemens has to pay for all the time that the machine is not operating, so they don't like that. Now, there are other solutions. The flame can also quench by itself because it's moving so much that at some point, whoop, it goes away. Same result, you have to stop the machine. The flame can go to another place. That's bad. It can move and stabilize at another place and burn everything there. That's also the end of the combustor. How do we know all that? Well, actually, because you are able, on this system, we can do active control. I'm not sure I have time to start that now. No, I think I'm going to do that tomorrow. Just want to flash the principle of active control, which is a little bit crazy, but when we did that, it was a crazy idea. You've seen here that we have this loop which creates combustion instabilities. So some people say, okay, there's a loop, let's add another one, which will actually play a role opposite to this one. And that's the principle of active control. The principle of active control is to add another control loop on top of this loop. How do you do that? For example, you measure the instability in your system with a microphone. And from that, you pulsate the injection of fuel with the white phase so that you can actually counteract the natural instability. So you add a feedback loop on the initial loop. And if you're good enough, you can actually kill the instabilities. That was developed actually in the 85 or something, 84. I think Cambridge did it first. We did it a year later. And it works extremely well. That's what I will show you tomorrow. You can actually completely inhibit these instabilities by adding a control system on top of it. And that will allow us to do other things I will describe tomorrow. So I will stop here. Any questions? Yeah. 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 You use the PDF at the previous time step, yeah, but you need a model for the PDF. That's the main problem.
Okay, so once we have that data, even though you assume some shape, you need it for different spatial locations, you need different like you need the movements of the precursor that
yeah.
For different places.
Yeah. At each place, you have a different PDF. And usually the PDF is a function of C and of C prime square, the variance. So you need an equation for C and C prime square, which will give you a field of PDF. The PDF will change as a function of space and time.
Okay, so you need to solve for those
Yeah, then you need to solve for C bar and C prime square bar. You need additional conservation equations. Another question? Yeah.
What do you think about the languages like Julia, which has like more development time used for GPUs and
Yeah, that's a big issue. We believe that in maybe 5 to 10 years, instead of having a 1 million line code, you will have a 20,000 line code written with what we call DSL, you know, one of these languages which actually have high order languages. The main problem today is that no one knows what this high level language will be. So it's difficult. We are exploring that, but we are not exploring it to the point where we take our production code and moving it to Julia or to Cocos or to all these things. But it will happen. In your generation, there will be a moment where you will completely give away on C++ and Fortran and move to this kind of language. The problem is to pick up the right one. And today, it's not clear. So if you get the wrong one, you're dead. Yeah.
One of the bottlenecks still seems to be the sequential time integration. If it takes 5 seconds to do one time step, maybe you run time steps, that's like a month of work right there. What are your thoughts on overcoming that?
That's a huge question, but physically, the problem of time-step integration is that it is difficult to imagine an implicit method where you take a flame or a vortex and move it 100 mesh size away from the initial point. The only way to do that is to do subcycling, which is like you would do in an explicit code. So at the moment, the compromise between what you gain in terms of number of iterations and what you lose in terms of the fact that each iteration costs a lot is not favorable for implicit. But it may become favorable, but today it's not. It's a big question. If you can do it, that's a good paper to write on that. I think it's tough to do it implicitly. Other questions? Okay, so
Sorry, could you talk something about the models used for
the weakest point of LES is walls. So please don't do walls. Now, having said that, it's clear that LES is great far from walls, but when you go to the walls, the large eddies become small. And so you are stuck again, and you need, what we do most of the time is to use law of the walls, because if you need to resolve the large eddies which are near a wall, which are small, then you have to do DNS at the walls. And so the weakest point of LES for aerodynamics is clearly walls. For combustion, it's not so much because walls are not so important in combustion. But it's only because they are not so important that we can do it. So we use law of the walls. In other words, we don't resolve the eddies near the walls. We model them, which is, again, you are using 5 PhD students to do that full time just because law of the walls with combustion is complicated. But we cannot afford to put the points there. It would be too many points. Again, at high Reynolds number, it would be crazy to resolve the walls. Okay. So thanks a lot, and we meet again tomorrow. Thank you.